Check. 1, 2, check. check, check.
So, good morning, everyone. Welcome to N2. Let's welcome our speaker, Mose, who is going to talk about decoding radio signals with radio clock. Super excited.
Thank you. Hi, everyone. I'm Mose Giordano. I'm a research software engineer at UCL. And this is a talk about a fun project. Probably it's not very useful, but it was a fun project for me to do. And it's about decoding radio signals, time signals using Julia. So if you travel to Mainz by train, in the train stations, you may have seen one of these clocks. And all the Deutsche Bahn clocks in the stations all over Germany are all synchronized all together, thanks to a radio signal, which is called DCF77, which stands for Deutschland, Germany, call sign for radio clocks Frankfurt at 77.5 kilohertz. That's the frequency of this signal. It's called Frankfurt, but actually the transmitter is in Mainflingen, which is just outside of Frankfurt, and it's about 55 kilometers from Mainz, so it's pretty close from here. And this is operated on behalf of the German National Meteorology Institute. The cool thing of this system of transmitting, broadcasting the time signal is that you don't need internet access, you don't need a GPS, which may be complicated to have, but you only need a very small receiver, like that one that I will show you later. And it's a very cheap system to set up. And this antenna has been in service from 1959, but it has been broadcasting the time signal from the 1973, if I remember correctly. It has a range of about 2,000 kilometers, so it covers pretty much all over Europe. This is not just Germany. And there are many other similar stations which do the same of broadcasting a time signal, but the protocol will be different. The frequency of operation is also slightly different, but there are like antennas in the UK, US, Japan, China, and so on. How DCF77 works. So you have a message which is 1 minute long, so it takes 1 minute to broadcast the time signal. And basically to give information, the message, the signal, drops the amplitude by about 25%, if I remember correctly. If the drop is 0.1 second, you interpret that as a 0 bit. If it drops by 0.2 seconds, you interpret that as a 1 bit. Actually, in the last second, second 59, there is no drop at all, so the signal remains constant, and this is how you understand that it's beginning the next minute. So at the end of this silence for about 1.8 seconds, you see, you know that it's starting the next minute. So the message is very slow, it's 1 bit per second, and the DCF77 gives you the following minute. Like the message, when it starts, it's transmitting you the next minute, so that when the message ends, it's giving you the minute now, the starting now. It's important because other protocols are opposite. Maybe they tell you the previous minute, so when you end receiving the message, you're actually getting the previous minute. So you need to know how the protocol works. This is the format of the signal. So you have the first bit, which is always 0, then there is some civil warnings bits, but I'm ignoring them because those are encrypted. You need a license to decode them. And then there is information about the summertime announcement, whether you're about to switch the time, the time zone, the daylight saving time, or you're going back to the normal time, the standard time. There are 2 bits to check that you are in the correct saving time or standard time. There is an announcement about the leap second, and then you have a bit to tell you, oh, now I'm starting broadcasting the date time information. So you have some bits for the minute, plus the parity to check the consistency of the message that you're receiving. Hours, again, plus parity. The day of the month, day of the week, the month, and the year in the century. So you only need the last 2 digits of the year. And then, again, some parity to check the consistency of your message, and then this silence. And now, to make it more visual, the message looks like this. So it is constant for some time, and then you have these drops. If the drop is 0.2 seconds, it's a 1 bit. If it's a 0.1 second, it's a 0 bit. But actually, receivers like that one are the opposite. So instead of having drops, have spikes, like you have a square wave that you're reading, But this is then the same. So if the width of this square wave is 0.1 seconds, is a 0 bit. If it's 0.2 seconds, it's a 1 bit. And then at the end of the minute, you have this silence for some time, which is how you know, oh, now it's starting the minute. So this is the beginning of the minute, this exact moment. So why I'm telling you this here at JuliaCon? Because I wrote a Julia package to decode this signal. So radioclock.jl is a pure Julia decoder and also encoder for the DCF77 time. So it has a data structure which represents the data. Since it's 60 bits, I'm using a uint64 to represent it, so I'm just wasting 4 bits, but I think it's fine. You can decode or also encode the signal. And yeah, if you want to, you can also pair it with like an Arduino and a small receiver like that to actually receive the data information, then date time information from the antenna. And also, since it's Julia, this is very fast. Like the decoding takes 50 nanoseconds, which I will say it's pretty good if you want to know the correct time and how it works. So you have here, you can load the package, and then if you have the sequence of bits as a string, you can pass it in the constructor, and then you can ask it to show you the time, or also actually the data object is also the pretty printing, which shows you the time and the binary representation if you want to double check it. This is time zone aware, so I'm using timezones.jl to actually get the time in the Berlin time zone, so that if you want to convert to your local time zone, you can just use the conversions in timezones.jl, and checking the summertime announcement using the time zones functionalities. I mentioned that the time signal has some parity checks to check the consistency of the data that you're reading, and I am also checking these when I'm decoding the data. So if the data is not consistent with the parity checks, you get some errors, which is usually very good to make sure that you're not reading garbage. I also mentioned that you can also encode the time. So if you construct a zoned time zone, zoned date time, you can encode it, so you get like basically the DCF77 data object that I showed you before. And this is very useful for me for testing, because I can do the round trip or checking that a zoned date time like this, it's converted to the bit representation, and then I convert back with the decoding to the correct time. And again, this is very fast, so I can actually check all the minutes from the 1st of January 2000 to 2038 in about 1 minute, and these are like millions of minutes. Yeah, implementation already mentioned this is using a uint64, and all the operations I'm doing are just masks or byte shift, so it's a bit shift, so it is super fast, and it's not allocating. And this also can be extended to other date time messages, like the US, the UK, the Japanese, and so on. Live demo. So, okay. I got a antenna receiver, which is this very small piece. I hope I didn't break it. I connect to the Arduino, and then connect it to my laptop through the serial port. So now I'm reading from the serial port. I started reading at this time, so I need to wait the beginning of the next minute to actually start reading the message, because I need to read a full message, right? So now I need to wait a little bit. And also, by the way, while we wait for this to finish, this is also the reason why if you go to the Deutsche Bahn sessions and you look at the clock, the seconds arm actually stops like moving for about 2 seconds at the end or at the beginning of the minute, because it's actually syncing with this. So every minute it does the same thing that I'm doing of waiting to check that the minute is actually starting when reading this message. I can also show you this. So, okay. So now we have the exact time from some website. Yeah, and this website is also telling me that the time on my computer is about 24 milliseconds off from the correct time, and then we will check whether the time that I'm reading is consistent with this information. So okay, so the reading has started, and now we need to wait when this reaches 10:11 to see the message, and hopefully the time that this gives me is the correct time. So we will expect to see the time to be 10:11 in the Berlin time zone. We are almost there. Yes. So this was off. So this was off by 47 milliseconds, but there was also a plus minus 19, so it's almost about there. But the good thing here is that the distance from the antenna is irrelevant because the time it takes the light to get to mines is less than 1 millisecond. But for example, in London, if I want to, I live in London, if I need to take into account the time for the light to get to London, it's about 2 milliseconds. So I will need to subtract always 2 milliseconds. This is the end of my talk. If you want to play with this package and you get an Arduino and antenna like that, you can do it. The package could be extended if someone wants to do something like this to other signals. That will be a fun project. And yeah, that's it.
And now we have some time for questions. Let me get to you.
Yeah, really fun talk. Probably super useful, but I loved it. My question is, have you ever tried listening to the radio signal, just like to the sound of it, and then putting in the zeros and ones, like as you hear the signal, to try to get it this way?
No, I never tried, but one thing that you can do is to read from the, I mean, this is what I'm doing. I'm reading from the serial port, and what you get is basically this. Boom, boom. So you will, if you wanted to put it in sound, you will hear some pulse. Boom, 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 boom.
You can hear the difference between the 0.1 and 0.2? So you think you can, like...
Yeah, like, you will make it longer, yeah.
To by hand put in the ones and zeros.
Yeah. Yeah, but this is going super fast.
Hey, thanks for the talk, very interesting. So I have one question that's possibly related to recent events. As you know, like in the Strait of Hormuz, we have had read reports about GPS hacking where they send out incorrect clock signals to confuse the ships as to like, you know, where they are or where, you know, like targets are heading and so on. So my question is there like a checksum or like anything that you can check for authenticity of this signal that you're decoding? Because it could be spoof, it could be like...
I'm not aware of any of that. The only thing is there are parity checks, but it's not really what you're asking. I'm not aware of anything like that.
And do you have to put in manual corrections for your distance from...
Yes, I was saying, for example, in London, I will need to take into account that it takes 2 milliseconds for that light to travel from here to London. But distances you need to do yourself on your end, and it's not, because the antenna is just giving you the current time in Frankfurt.
Thank you. Just quickly, have you checked the other radio signals from US, Japan? Are they similar or?
So the protocol will be different. My problem is that I don't live in Japan, so I don't receive the signal. and also I will need to find one of these receivers. Because, for example, there is one antenna in the UK, but I didn't find on the internet one of these receivers. So if you can help me find it, I can test the UK signal, but otherwise I'm using the German one.
Okay. We're almost at time, so is there any other question? Or
That was...
just the final one.
I was just going to ask about the American one, the WWVB. Is that structured similarly to this, where it's some type of repeated binary signal? 'Cause the
So
only-
I believe all the signals are like 1 minute long, so, but the bits are encoded differently.
Okay.
And also, I believe it's the American one, which gives you the previous minute. So at the end of the message, you're getting the past time,
Okay.
which is a bit odd. But
Because I didn't know we offered one of those,
Yeah.
because I've only ever heard the
yeah,
audio.
so actually, my watch can read the German, the UK, and the Japanese signals, but in the US, I've never been able to receive. I think the antenna is in Denver, but I've always been on the East Coast recently, and I was never able to sync the time with that one.
Okay. Our next speaker is ready. So let's thank our speaker again. And now, sorry. So we're going to hear Gia Bunusali. Did I say that correctly? Banusali, okay. Talking to us about modeling cost sustainability trade-offs in maritime logistics with a focus on EDI-driven multi-objective optimization. The floor is yours.
Okay. Hi, everyone. My name is Gia Panushali, and I'm going to be talking about the inherent cost emissions trade-off that takes place in shipping. So first of all, I would like to acknowledge my co-authors, my mentors. They introduced me to Julia. They taught me everything that I know. So Professor Vijay Dixit and Vaibhav Dixit. So first of all, I would like to talk about why this is so important. And I would like everyone here to take a look around. The mug in front of you, the laptop that you're working on, the steel in this building, everything probably cost a ship to get here. But there's also a caveat. So shipping is responsible for close to 3% of global greenhouse gas emissions, with this number increasing every single year. Now this is a proper decarbonization problem that we're tackling. So I just want to jump right into the applications in Julia. So the overarching package that we're using is JUMP. So we're using it as a modeling toolkit to have different solvers interact and help us solve the different aspects of the model. So MathOpt interface essentially acts as the layer that connects all of the different solvers that do their job. Then we have 3 different solvers. So we have a Juniper as the overarching MINLP driver. We've got IPOP and GLPK. So IPOP takes care of the nonlinear aspect of it. GLPK is for integer decisions. And finally, we use Kairomaki to get some pretty Pareto frontiers that I'll be showing later. So this is the code snippet of what the solver setup looks like. It's pretty, standard, and I do hope to use faster solvers like Heis and Kurobi in the future. When we come to the decision variables, these are some of the most integral part of the model. So the first 2 decision variables, the fuel mix and digitization, act as decarbonization levers that I'll talk about in the further slides. The regional assignment represents a binary decision variable that decides where your ship is going to end up based on demand and regulatory policy factors. Then we talk about the demand slack. So say, for example, your ship is assigned to a region where the demand is over or under allocated based on cargo capacity. So you're obviously going to lose out on the business, right? So this is how we tend to model that in the model. Then we come to the EDS credits. So we use a EU-based cap and trade EDS system, wherein we model it as a continuous decision variable to show how many credits you have to buy or sell based on the amount of emissions. Then we come to the first decision variable that I'll talk about in detail. This is the operational levers for decarbonization, so digitalization. We're taking 6 overarching digitalization levers that help shipping companies to decarbonize by improving fuel efficiency, enhancing documentation, as well as reducing port idle times. So these are pretty self-explanatory, but please feel free to ask me later if you have any questions. Then we come to the marine fuels. So here, the cost emissions trade-off becomes more and more obvious because marine fuel is responsible for 60% of total shipping spend. And these fuel options go from dirtiest to cleanest, but least expensive to most expensive. So the trade-off is clear. It's like if you take the cheaper fuel, you're ending up burning more of it and it's dirtier. But if you're taking the more expensive one, you end up having to pay more, but you end up with less emissions. So now we come to the parameters. So the data used in this model to validate is actually rooted in regulatory documentation, industry report, benchmarking, because we did not have access to suitable publicly available data sets. But this has been reviewed and checked by industry experts, so it's fine. Then we also modeled it as native Julia dictionaries and hard-coded it into the model because of the size of the data set. But later on, in the future, we're planning to add a CSV extension, so something that can take data directly from existing files. We come to probably the most integral part of the model, which is the objective function. So as I mentioned, it's a bi-objective model, so we're optimizing both for the total cost function as well as the total fleet emissions, so it makes it a fleet-level framework, and this is how we model it in Julia as well. Then we come to the constraints. So now, decarbonization policy is becoming increasingly stringent due to the nature and probably how important shipping is when it comes to trade. So these are the two major regulatory constraints that translate this decarbonization policy into indices that can be measured as metrics. So these are the energy efficiency design index, as well as the energy efficiency existing ship index. So the energy efficiency design index is calculated at the time of ship design, and it takes place into consideration the specific fuel consumption, the deadweight tonnage, and things like that. But whereas the energy efficiency existing ship index, what it essentially does is it measures the same metric for existing ships. So what happens is you have a reference EEDI values are set by the regulatory authority, and they tell you to reduce the EEXI by X amount every single year. So your ship keeps on getting more and more efficient. Now we come to the other constraints. So these constraints are just operational and other market-based constraints that have been translated into the mathematical model. So in this, I've used the iterate constraint option in JUMP to model it as well. Then we come to the methodology. So a naive epsilon constraint sweep method is probably what you would use in a multi-objective optimization problem. But what it can do is the weak Pareto optimal points can often end up on the Pareto frontier. So what we do is we use an augmented epsilon constraint method, which basically takes two anchor points. One anchor point optimizes costs without taking emissions into consideration. The second one optimizes for emissions without taking costs into consideration. So you have a nice range where you can just split it into a range of 10 points, optimize cost by taking augmented emissions as a constraint, which you'll see in the code snippet that I'll be talking about. And then you just have a nice, easy, feasible region to sweep and get a local optimal solution. So this is how it works. You have 10 points, a range. You have an augmentation weight that's been given, and then you can just sweep in this range to get your Pareto frontier as well. So Kairomaki has been used to implement this and to give us the Pareto frontiers, not just off the total cost, but as well as all the different cost components. So you can see how the different cost components are affected by the emissions and where you need to optimize. So this is all about the mathematical mumbo jumbo. What does the model actually do? Imagine yourself as a ship owner. You have 10 ships, you have not a lot of money, and you have a little bit of fuel constraints as well. So you give me your data, and I give you this. So I tell you, I don't know if it's visible, I tell you what kind of fuel to use, and what kind of digitization retrofits to make in the ship, and where the ship should go. After that, you can see the total cost, total emissions, and the entire breakdown of all of the fleet cost components as well. So this functions is essentially a rudimentary decision support tool that will be developed into a GUI-based tool in the future, and maybe even commercialized. So now I come to the sensitivity analysis part of it. So what I've basically done is created all the possible combinations of the digitization levers that are possible. So I really understand what's the marginal benefit of having, say, one more digitization option. Are 2 working better than 6 in some places? Or do you need all 6 to be the most compliant that you can be? So from Julia, it basically demonstrates a very niche and concrete use case for Julia in the maritime domain, which is where Julia is very underexplored at the moment, as well as it can be developed into a GUI-based decision support tool, as well as a package. To maritime logistics, usually these regulatory constraints, fuel optimization, route optimization All of these things are usually studied in isolation because they're so deep as fields in themselves. But our model takes these levers into consideration as an entire digitization ecosystem, so you can study them as an integrated fleet-level framework instead of trying to integrate different isolated pieces of computation. So that's all about my talk. This is my LinkedIn if anyone wants to connect, and I'll open the floor for questions. Also, I completed early, so I can take more questions.
Thank you very much. Okay, we have a question here, and I have a few.
Okay, yeah, sure.
I'm from Greece, that's why.
How common is it for ships to be easily retrofitted to run on multiple fuels? Because as far as I'm aware, if a ship runs on heavy fuel oil, it's running on heavy fuel oil for its entire life. How common is that?
The thing is, what happens is with newer and newer ship design, as these regulations become more and more stringent, there are engine retrofits that you can make to make it, say, methanol or LPG compliant. So for older ships, that's not possible. But with the newer ship design, as and when it goes by, it is becoming increasingly possible to at least, if not have a complete voyage on methanol, at least have partially bunkered fuel. Yeah, please, next.
I will, like, as a naval engineer, which I'm not exactly, but I'm partially, if you have a ship that takes heavy diesel oil, it will happily consume pretty much anything else with very little changes. The heavier fuel is, it's easier to give it better fuel.
Okay.
So I have a question, like, have you tested this on any, so there is a dimension of who asks for like you have a ship and someone asks for a trip. Have you used it on any operational data from big traders of routes, like Trafigura or someone like, have you tested on operational data? Like, do you have feedback from the market?
Yeah, so it was really difficult to get actual operational data because shipping is very closed off sort of industry in a way. So, but the thing is, we did contact a lot of industry experts to get their sort of, because they deal with so much data of this sort on a day-to-day basis. So we were able to sort of have them review the data and make sure we were going in sort of the right direction. But in the future, when we're trying to create the decision support tool, then if, for example, if we're collaborating with a shipping company or such, a shipping provider, then obviously they will have to give us the data because they want our tool. So.
Sounds great. Do we have other questions for our speaker? Perfect. I have more questions.
Yeah, for sure.
Thank you. Do you think it's easy to extend it for safety? Because often ship owners will, for example, avoid the Suez Canal, and maybe that is a third dimension?
Yeah, definitely. Because the thing is, right now with shipping, the supply chain shocks are becoming increasingly more, sort of vulnerable because of a plethora of factors. But definitely, if we're able to get that kind of data, then maybe in the real-time basis, we could optimize to make the route safer as well. And then we would integrate that routing and geospatial aspect into it. Because if I'm able to get real-time data of which route is the safest, and obviously I will prefer to send my ships there even if it's more expensive, Does that answer your question? Okay.
Okay, the next speaker should get ready. Do we have any other questions from the audience? No?
Yeah.
Okay, let's thank our speaker again. And our next speaker is Anshul.
I seem to be a bit cursed. There we go. Okay. Hello, everyone. I'm Anshul. I do a bit of work on Maki.jl. In my day job, I work on Dyad, which is Julia Hub's modeling and simulation product. And I wanted to come here today to talk about how you can make things that you should keep in mind when making engineering visualizations with Maki. So if, for those of you who don't know, Maki is a data visualization library in Julia. It's got a bunch of backends. It can do OpenGL rendering, vector rendering, all this sort of stuff. But the cool thing about Maki, I think, is that it works on this model of observables. So basically, if you look at these 3 lines, these are all relatively familiar to people, right? You'll have seen these in Matplotlib, plots.jl, things like this. You're creating a top-level figure, you put an axis inside it, and you create a plot series. But the cool thing about Maki is that after you've created this plot, you can dynamically update its attributes, right? So I've created my plot, and then I can say, okay, I want you to make the color of this plot tomato. And when you say that, then that update basically proceeds to update the smallest number of things possible on the GPU or in the PDF or so on, in order to very efficiently and in real time make that update. So that was Maki, right? And so Maki has a bunch of different backends. So these are different. Maki is the front-end library that you would interact with, and then the backend is what renders things. So you have Cairo Maki for vector export, and I think GI just showed us some plots from that as well. GL Maki for fast interactivity, so that's running in OpenGL on your desktop. WebGL Maki allows you to put things on the web locally, but also to serve it over the internet. And then, not quite released yet is this Ray Maki backend for ray tracing, which I'll show some ray trace plots as well. But the idea is that Maki is this really nice front-end language, but it is a single way to describe a lot of different visualizations. So you have one entry point for both your publication plot and your small little dashboard that you threw together on the fly to understand your system. So, it seems that, unfortunately, my computer has sort of gone through a couple of power issues recently. Okay, so this was supposed to be a live little dashboard that I would show, but when that happens, it will happen. Okay, so visualization is how we understand and interact with models, right? So anytime you do anything, it doesn't have to be a model. It can be any scientific paper. It can be any problem that you think about, right? Most of the time, the answer that you see is going to be something visual, right? You'll see a plot. You'll see maybe a little video. And so these allow you to notice patterns, to notice failures, to compare things, and to explore things. So there's a lot of different things you might want to see, and I'm going to sort of focus on the what you would sort of call the ODE or DAE kind of modeling. So I'm not focusing so much on three-dimensional stuff, not so much on PDEs, although those are still things you can do very easily. So one thing you might want to do is to plot a bunch of variables and analyze them, right? So you can see here, all right, here's an RLC circuit. You've got a voltage trace on a capacitor. You've got current, but then you can also derive the stored energy in the capacitor, right, and plot that. Or you might have run a large parameter sweep over a bunch of parameters. You can say, okay, if my resistor in my circuit has a 30 ohm resistance or a 300,000 ohm resistance, what's going to happen? And you can plot that frontier, and you can say, okay. Visually, you can build an intuition for what's going on. But it's not just static plots, right? You can have animations, but then you can also have interactive dashboards. And so I want to show a small example of an interactive dashboard that I made some time ago. And I've shown this a lot, so I'm now promising myself that this is the last time I will show this in a conference. I have to come up with something new next time. So what this is this is a bunch of satellites. Is this visible to everyone sort of clearly? Sweet. This is a live dashboard, right? So the simulation is running live as I'm showing you this. And the dashboard is all made in Maki.jl. So this is a live dashboard of a bunch of satellites orbiting the Earth. And you see this little blue dot here. This is a ground station. So the satellite will communicate with the ground station. And you'll notice that the power stored in the satellite sort of dips every time. And we also sort of plot which ground stations are getting contacted here. And you can also see that there's some change in thermal state. I can increase the power draw of the CPU of the satellite. And then you will see that every time some of these satellites are facing the sun, which I didn't show here, that their solar panels get quite hot. So there's multiple dimensions of simulation going on here. You have your power system, you have your communications, and you can show all of this in one dashboard, right? And you can understand things. I can speed the simulation up, slow it down. But this dashboard is made using the same language that I would use to describe a static plot. And I think that's the really cool thing about Muschel, is that I can go directly from, I think this paper is cool for publication, to let me just add one little slider on the bottom and change one parameter just to see how it works. So, here we go. Yes, perfect. Okay. So here's another interactive dashboard, but this time it's doing more analysis. So I have some, some trajectory here of some solution. It doesn't really matter what. And I can move the slider around. So this is actually a local web server that was spun up with WebGL Muschel. And I can move the slider around to then basically analyze my trajectory. And this is pretty simple. Of course, you could imagine doing more complex things. And you can see that that is changing what I'm seeing live. So I can, I could sort of build some understanding of, all right, these are the thresholds. Let's say this is some voltage threshold. I can't supply more than this. In my simulation, these are the places where my system is exceeding that power threshold. And therefore, I need to investigate these time points to see what's happening and decrease the power consumption. So when you do these kind of web dashboards, one thing I did want to note, it's sort of very easy to make it for one person. But when you make something that's meant to be served to multiple people over the web, it gets slightly more difficult. So one little piece of advice that I would have to keep in mind here is you always think of, you can sort of think of shared versus global state. So let's say I have a live simulation running, and that live simulation is the same for everyone. Then that live simulation becomes my global state. But whatever I'm trying to analyze, if that's a per user thing, then that becomes my local state. So this is some pseudocode from bonito.jl, right? So every time a new user opens, or a new browser opens this web page, it creates this new thing called a session. And so in every session, you can instantiate the particular local state that you have. Another cool thing that Muschel has introduced pretty recently, I think in the last 6 months, if I remember, is this thing called a compute graph. So Muschel previously worked on this idea of observables, which were single values that when you change them, they would send a signal out to a bunch of listeners that could then propagate updates down. The problem with this is, what happens if you want to update two things at the same time, right? I'll put this figure up on the Muschel docs as well, because I suspect it'll be useful. But what happens when you try to update two things at the same time? Well, in observables, you had several workarounds. You could change the value of one, but then only propagate the update of the other. But it was all very convoluted. So with the compute graph, we create this graph structure, right? And we add certain inputs. Then this map function is basically what allows you to sort of register or declare computation. So you're passing it an anonymous function, and you're saying, these are my inputs, right? These are the inputs that I consume, and this is the output that I create. And you can have multiple inputs, multiple outputs, as you want. So the last thing I'm going to mention, and while this plays, we can probably also take some questions. Muschel and AI are very good at creating infographics. So this is something I made for fun for a project that happened at a place I was interning in. I just made this a month ago or so. And this is illustrating basically a data processing pipeline. And so how you acquire the data, how you process the data, and sort of what's going on. But if you have any sort of project that you want to tell people about, or that you want to make seem very cool, AI plus Muschel can be pretty good. So yeah, thank you, everyone. And I think we have some time.
Yeah, we have 6 minutes for questions.
Nice.
That was a great talk, Anshul. Thank you so much. Okay, we have our first question. Let me come up there.
If it's easier, people can also just yell out the questions and I repeat them.
Okay, I can yell. Thanks, Anshul. So when you say making an AI is good, which AI are you talking about? Because apparently there are all these flavors of AI, and actually my flavors of AI are terrible with Muschel, so I should find a better one.
So you should come to my talk at 4:30, where I talk about exactly this. But in all seriousness, I found that OpenAI models are usually the best at visual things. Anthropic models are usually the best at sort of architecture and understanding code. But when it comes to visual things, I generally use OpenAI.
Well, 1 second.
Yeah.
Yeah, really great talk. My normal workflow is like, for like quick and dirty plots, I normally use plots.jl, and then if I want it to be fancy, it's in Marquee. Is that just a skill issue on my side that I'm not good enough in Marquee to like do the quick and dirty in Marquee as well?
No, I think it is a good point, right? Plots was designed sort of from the ground up to be the library for quick and dirty plots. You can just call plot on basically any object and it will plot. Marquee was not designed with that in mind initially, although we're trying to sort of get there. You can poke these 3 guys sitting at the back if you want to know more. They're the Marquee developers as well. And no, but I think that Marquee does have a little more bookkeeping to keep track of, right? When you create a plot, you get a figure, an axis, and a plot, and so on. For most things, it should just work now. So you should be able to call plot on a lot of things and get a result, but there is a little bit more bookkeeping. So I don't blame you.
Okay, next question. Yeah, George.
Thanks. When you made one of these dashboard-like apps, you explicitly said that you made it on the WebGL version. Although to me it looked like a GL Marquee window. Do you have any advice when I should prefer to do one or the other?
Yeah, so the satellite app that I showed was actually GL Marquee. It's just the little slider thing which was not. Generally, I would say, so there is one thing that I didn't show here, which is that there are some situations you'll get into where either you want to serve the dashboard to someone who is not like on your computer and is not able to run that code, or you have something backed by a large, powerful server, for instance. So that's one instance where I would use WebGL Marquee. The other instance is where you want to have JavaScript code and JavaScript-based graphics alongside your Marquee plot. So for instance, if you have, for Dyad, we have a graphical interface, right, which allows you to construct a model. And so if I want to use that model to influence my plot, if I want to be able to click on a component and say, plot this variable from this component, that's also when I would use WebGL Marquee, is to allow coupling between JavaScript and Julia.
Hi. Thanks for the talk. Can you show the slide where you map certain variables to the GUI components?
Sorry, could you say that again?
Can you show the slide where you map some parameters to be like a dragger?
Oh, yes.
Like, yeah. How is it done easily?
How easy is this? So it sort of depends on, so to set this up is quite easy. Of course, the analysis of what you're doing to create the visualization can be as easy or complicated as you want. But basically what you do here is you create so Marquee has a UI toolkit inside it. So you create a slider, and then you can listen to the value of that slider and then change some other variable, which eventually then gets plotted.
So we have 2 more minutes of questions, but the next speaker should be preparing if that's possible. Do we have any other questions for Anshul?
If not, I can also show some, if we have 2 minutes, I can show a little bit more inspiration.
Yeah, that would be great.
All right, so this is a cool little video I made with some ray tracing. So this ray tracing was actually not from Marquee's library. This was from basically I hooked up Marquee to NVIDIA's ray tracing renderer called Omniverse. And so on the left-hand side is the ray tracing, on the right-hand side is GL Marquee. They're both rendered together. And so basically what this is a car driving over a bumpy road. And you have this very visual depiction of a car, right? So I can see this bumping, and what we're really interested in here is the suspension. And I can see this sort of bouncing, and I can really feel, oh man, this is a terrible road, I hate this thing, why did I go here? And, but you can see on the side also some metrics which could be interesting for example, developing the control system for the suspension, right, or things like that. Another cool thing, so just to sort of talk about, this idea of like having a single grammar where you can do a lot of things. This was the initial video I made of a car, right? And so this is rendered in GL Marquee. This renders very quickly. It renders on most systems, and it looks decent. But I could go basically directly from there to this, which with the exact same plotting calls, right? Okay, the scenario is a little bit different. I have another picture of the exact same, the old video, but in the ray tracing rendering. The scenario is a bit different, but this is the exact same language. I just changed the rendering backend. So I think that's sort of the power of Maki that I was trying to get across, right? That you can do these different things. Okay, I think I'm out of time.
Yeah, super cool though. And
Thank you.
It sounds that you need to do a webinar.
I did one already, but I'll do another.
Thank you very much. And so let's welcome our next speaker, Matthias Franz. I hope I'm saying that correctly. Will talk to us about formal linear combinations in Julia with linearcombinations.jl. The floor is yours.
Do I get a sign 5 minutes before the end? Oh, and this is 5 minutes before the questions. Okay, good. Hello, everybody. Yeah, I want to talk about formal linear combinations. So this is a kind of a pure math talk, an application of Julia to pure mathematics. So what is a formal linear combination? That's something that occurs in many, many parts of these pure mathematics. You just take a bunch of terms, decorate them with coefficients, and then write this as a sum, but it's a sum that you never execute. It's just a bookkeeping device. Yeah? You can think of a polynomial as a linear combination of monomials. In this case, would be the monomials 1, x, and x cubed. In my field, algebraic topology, we look, for example, at simplicial chains. So you want to study geometric objects by cutting them, for example, into triangles. So here's a square cut into 2 triangles. And then I can say the whole square is the formal linear combination of the triangles ABC and ACD. That covers the whole area. Okay. If I know which terms can appear in my linear combinations, that means if I have chosen a basis, then of course it's enough to record the coefficient vector, which will be the coordinates of whatever linear combination I've constructed with respect to this basis. Yeah? So for the square, it would be the coordinates 1, 1 with respect to these 2 triangles. Okay. Now linear maps. Yeah? Linear maps between vector spaces, or here free modules, are determined by what they do on a basis, and conversely, I can send the basis vectors to any vector, and then this will extend to a linear map. Yeah? So here's an example. If I know how to differentiate a monomial, then I know how to differentiate polynomials. Yeah? For the triangle example, an important operation is to take the boundary. Yeah? So the boundary of the triangle ABC is the edge AB, and then BC, and then you go from C to A, and it's better to record this as the edge AC with a minus sign for the reverse orientation. And once you know this rule, you can compute the boundary of the square, and the result is what you expect. You go from A to B to C to D, and then you do AD in the opposite direction. Yeah? Of course, once I have chosen a basis, I can represent my linear map as a matrix. So you see on the screen the matrix representing this boundary operator. But for this, I need that the bases that I use are actually finite. Now, if you think of the polynomial example, every polynomial is the sum of only finitely many monomials, but infinitely many monomials can potentially occur. Yeah? And so it's a bit tricky to store this as coordinate vectors. You would have to say at the beginning of each computation, what is the maximal degree of the polynomials that can occur during your computation. Yeah? That's at least annoying. But even if you can do that, yeah, you don't really want to do it because it's not natural in a way. In this boundary example, if you ask me, well, what's the boundary of the triangle number 2 in the basis, then I would have to ask, first of all, what triangle is this, right? But if you tell me that's a triangle ACD, then I can immediately tell you what the boundary is because I have all the information that is needed. Yeah? So it is either necessary or at least very convenient to deal with the formal linear combinations themselves instead of doing it with coordinates all the time. Okay, that's where my package comes in. The goal is to implement linear combinations in Julia. I'm sure I'm not the first one who has done this, but I'm not aware of a package that does it in a general way. I think many package authors have created linear combinations for their specific purpose, but you cannot reuse the code. And here the goal is I needed it for this triangle example, if you want, and do it in a reusable way. Users can deal with linear combinations with arbitrary terms. Well, underlying the linear combination will be a dictionary, so it has to be hashable, and arbitrary coefficients, which I assume to be commutative. So it could be the integers, rationals, integers mod n, whatever. Okay, and then on the slide you see how that then works. You create a linear combination by giving the terms that occur together with the coefficients, and then you can do computations. So B is the term y minus the linear combination A. You have promotion of coefficients. If you have a big int coefficient and a float coefficient, then this will be promoted to big float. You can ask for the coefficient, say, in front of x. This is 1. The coefficient in front of z. Well, there is no z, so the coefficient is 0. And the length is the number of non-zero terms. You can iterate over a linear combination, which will iterate about the terms and the coefficients of the terms that occur with a non-zero coefficient. Broadcasting is also supported out of the box for linear combinations. If you, in your broadcasting operation, you want to have individual terms, then you need this macro linear broadcastable because you have to opt into a certain broadcasting style. And if you do this, you can in particular do in-place modifications. So A dot plus equal B and so on would take the linear combination A and modify it by adding the combination B to it. And then 3 times the vector z. Yeah? Okay. You can map linear extensions. You can define linear extensions from terms to terms. You can have here a function that computes the uppercase of every character. You make it linear with a macro linear, and then it extends automatically to linear combinations. You can also map linear combinations to linear combination. You can map each term to a linear combination. That's what the function g would do, which each term to a linear combination, and then again, it extends. Yeah? You can also do dense linear combinations. This is the coordinate example. Yeah? So here, everything under the hood would be done with coordinates. You can ask for coordinates and so on and so on. That would be much faster, but we have discussed the problems of this approach. You can have matrix representations of a linear map once you have chosen bases. Maybe I skip this now. Other features of the package, you can have linear functions without intermediate allocations. I talked about the example of the function g, which assigns a linear combination to each term. If you evaluate this on a linear combination, there would be a lot of intermediate linear terms that are created, linear combinations. You can avoid this with a special syntax that would then reduce in very few or even no allocations. So far we had linear functions. You can also do multilinear functions. For example, the product is bilinear by default, and then you have, it would multiply it out. You would have tensors in the sense of pure mathematics. So these are, if you want, universal multilinear operations or formal concatenations. And then you have this. There's actually a lot of code in the package for tensors. You can have the Koszul sign rule and so on and so on. Then maybe some benchmarks. I was asked to do benchmarks, to talk about benchmarks when I sent the proposal to this conference. And it was a bit difficult because I don't really know other Julia packages that do this. So there's symbolics.jl for general symbolic computation. And the closest that I know of is in Sage. There is this combinatorial free module, which is very much like this package. So I'm comparing it to Sage, and I really only need symbolic utils from Symbolics. And they are thanks to Ayush Sabharwal for telling me how to program this with symbolic utils. And you see here, I take linear combinations. I take, with several hundred terms, the partial overlap, and I add them. And I have a linear map similar to this function G that I showed before that maps each term to 2 terms. And you see, maybe first for Sage, I think Sage uses big ints, so for sums we are twice as fast, for linear maps about 8 times faster. And for symbolic utils, it is much more striking speed up, but again, symbolics.jl can do much more general things. This is only for linear combination with a goal to do this in a really fast way. Have in mind, you might have linear combinations with thousands, 10,000s of terms, and then the thing gets really fast. Yeah? If you want to see it in action, check out my package Simpliciter Sets, which generalizes in a way the triangle example from the beginning and shows more or less all features. Okay, to close, let me just say, when I talk to colleagues who are only vaguely familiar with Julia, and I say I'm using Julia, then they would say, oh, isn't that just about numerical computations? So that's the perception that is out there. I think Julia has a lot to offer for algebra and other parts of pure mathematics, and I hope this package can contribute to this. Okay, thank you very much.
Thank you very much. That was a very interesting talk. Let's see if there are any questions, and the next speaker should be preparing to.
So, yeah, very interesting. Can I also use this to define a group ring? So, but have multiplication then, or?
Sure. If we go back to this multiplication example here in the middle, yeah, if you have a multiplication defined for terms, then because this is the bilinearity is already defined, it would out of the box work for group rings. Yeah, so that's the idea. You only define your method for terms. If it's a new function, then you have to add this method that makes it linear or multilinear. That is one macro, and that's it. Yeah? And in this case, if you define a standard symbol, well, it's just, the multiplication is just baked in that this will be multilinear with an arbitrary number of factors, and then it just works.
Thanks.
Okay, any other questions? Yes.
Thank you for a great talk. So how is the compatibility with the other symbolic packages in Julia? Is it possible to convert back and forth depending on which type of problem you're tackling?
For the applications that I had in mind, because of the benchmarks that I've shown, and also because, say, symbolics.jl has to be truly symbolic objects, I guess, and I want to use, like, for the triangles also on, it's not really symbolic. So in this sense, I haven't really studied that. I would think there are two ways. If you can represent everything in coordinates, then I've shown you can immediately convert, does a wrapper around your coordinate vector that gives you a linear combination. Otherwise, you use this constructor linear and just feed it in, and then you would get it out, and just by looping over it, you could then transport it back and construct the representation of that you have in another package. But at the moment, there's no method via, I don't know, package extensions or so that provides the link to other packages. But it will be a very interesting thing, yes.
Okay, Thank you so much. Any other questions? Okay, then we'll move on to our break for 15 minutes, and we'll be back in 15 minutes with the next talk, which could. We are on time, so we should start. Yes. Okay, let me introduce our next speaker, Christian Kutsche. Okay, will talk to us about introducing context.jl, a context and role-oriented programming for self-adaptive systems. The floor is all yours.
All right, thanks. So I guess most of you people won't be so familiar with these concepts of context and role-oriented programming, since those are very kind of niche programming paradigms coming from object-oriented modeling and programming. And that's why I try to start with a example that why I hope this will make it clear. So like look at a smart system, like a smart home. What you normally have that you want to operate it depending on like the external state, like the environmental state and the state of the house. So you have a lot of influences like the weather, like cloudiness also, the temperature, maybe also the residents' activities, things like the electricity prices, air quality, but also internal things like the state of charge of the battery or the electricity consumption. And based on all these things, you would then want to operate your system, like charging, discharging the battery, operating your heat pump, and so on. What makes it even more complicated than only this high dimensionality of the problem is that you, of course, have some kind of feedback, so that if you operate your battery, you also change the state of charge of it. I'm in the software engineering field, and there we call these kind of systems self-adaptive systems, so when they have to adapt their behavior automatically according to the environment. What you normally do then is that you implement some kind of feedback loop. Very often we talk about the MAPE-K loop here, which is from a paper from 2008. And yeah, so this is basically just saying, okay, I have to monitor my system, analyze its state, plan the adaptation, and then execute them. And all of this somehow coupled to a knowledge base that helps me doing all of this. Very often we have these kind of systems in cyber-physical systems where we really want to change a physical system based on software, like the smart home or some robotics applications. And in my research, I was thinking, okay, let's do that in Julia. Why did I think that? Well, actually, even if Julia was designed for some completely different application case, it's actually quite nicely suited for that. One thing is the multiple dispatch. So we can have many parameters that might impact the dispatch and thereby the chosen behavior that we implement. So thinking about a smart home with all these environmental things, this is some way to address it. Also, like the dynamic evaluation we have with JIT compiling is very nice because we can make decisions at runtime and adapt the behavior automatically due to that. For like the software engineer in me, also the meta programming was really important because with that we can really nicely add syntax to the language, make domain-specific languages within Julia, and by that make it easier to define these complex systems. And also actually the whole simulation infrastructure that we have with modeling toolkit and all these things, it's really nice for working on cyber-physical systems here. I mean, I also want to be honest that Julia probably is not the perfect language because for the common software engineer, there are some design decisions like limited encapsulation or that you can't really inherit structure that might have a drawback, but yeah, I will ignore this for now. So coming to the first part, the context-oriented programming that I implemented. So what is that? Well, when we go back to our smart home, we can say we have all these different influences from the environment and we can abstract them into discrete categories. Like we can say, okay, the cloudiness can be sunny and the temperature can be warm and we want to cool down our system, our smart home by the AC system, for example. So this is some kind of discretization that we call context Another example would be that I can say electricity prices are high and the battery state of charge is high. So I want to discharge the battery in order to make money. Yeah, this is the concept of context, basically. And there's a whole programming paradigm that circulates about that. So in 2008, again, Robert Hirsch felt that I was proposing context-oriented programming, which relies on 4-dimensional method dispatch. So, just to remember, you like an object-oriented program, you would have 2 dimensions, the method's name and the receiver of the call, like its class, basically. And he proposed to add 2 more dimensions, like also the sender's class and some context, which basically you can define methods for multiple contexts and then automatically evaluate which context is active and call the function that fits to that. And as Julia programmers, you, I guess, noticed that this is quite free in Julia because you can, with multiple dispatch, define as many dispatch dimensions as you want. You can, what you need is to do, you have to specify context-specific types and then create objects of these types, singleton objects in the best case. And then you can use these types and objects to define and call context-specific functions. So this is actually quite easy in Julia. So this is basically what I modeled with context.jl in the first place. Additionally to that, I introduced a concept called context groups, where you can say, okay, there's a context group weather, and inside that group there are contexts like sunny, rainy, cloudy, whatever. And you can then reason at runtime about which of these which of these contexts is currently active. What you can then use to call the function that is defined for this active context. As a side remark, maybe you can also define logical operations on that, so that you can say, okay, if sunny or rainy, do something. Then I already mentioned that I added some kind of small DSL for that, so I created a macro called add new context where I can specify those, and just using a function on the context group class basically or struct to also define the groups. With the macro, you would then just create this kind of context-specific type, its singleton object, and add this to an internal database for managing all of this. And with that you then can also just call deactivate and activate sunny and cloudy, for example. However, what you then maybe notice is that there's an issue with context that shouldn't be active simultaneously, for example. So the library also tackles this problem by something called context relations. So for example, in the weather context, it's not only that they shouldn't be not active at the same time, but also there should be exactly one of those contexts active at the same time. So you have a kind of XOR relation that should always be true. And you could also think of something like, always when the context sunny gets activated, I want to deactivate my light for saving energy. And this is something we defined with these context relations. So you can define something like alternative rules, weak inclusion rules, requirement rules, and so on, simply by calling this function. And what under the hood then happens is that you actually create some control mechanism in the form of a patron net, which ensures that these relations are kept true all the time. I don't want to go too much into detail on that, but that's how it's controlled, basically. So to define the context-dependent behavior, I also added macro-based syntax with this add context macro. So you can basically add here like a tuple of context that will be then basically just added to a new attribute of the function, like a context of a tuple light off context type and human in room context type. And then when I call these context-specific functions, I can use the very same macro which then just adds the according values again, like in this case, the light and occupancy context groups, and of course at runtime this then will evaluate to the currently active context, and by that cause adaptive behavior actually. So to show a more practical example, I actually decided to not use this, but another thing I did with combining this context modeling with simulation, with modeling toolkit to be exact. So, well, I again designed a small DSL where you can say, okay, in one context, the system should behave like this, and another it should behave another way. And you can then define, like in the skeleton part here, all these variables, components, and so on that are true for like every context. But then I can also add context-dependent components, like for electrolyzer active and electrolyzer standby. In this example of an energy park, we want to create green hydrogen. Then actually what would happen is that SAT solver is resolving all these possibly occurring combinations of contexts that are allowed to be active at the same time. And at runtime we can then activate and deactivate context using callbacks and reinitialize the equation system. And well, here you see the results from such a simulation. You can see that, for example, the battery here in red is sometimes charged and sometimes discharged. Also the electrolyzer gets activated and deactivated, and all of this is basically defined by our context model. With that, I'd like to go to the next part, the role-oriented programming, because one niche modeling tool is not enough. Why did I decide to add this as well? Look at a swarm of robots. In this case, you would have, like, for every robot, some kind of context that should be define how it should behave. However, this context also don't only exist for the robot itself, but it somehow relates to all the other robot states, because they somehow have to act as in a swarm. And for these kind of relations, it's very hard to define a context model. But actually, we thought, okay, we have some concepts in object-oriented modeling and so on, which might be more suitable for this kind of problem. And here I'd like to introduce role-oriented programming. So what you would do in object-oriented modeling is that a person is some kind of class, and you would then, when you want to model a student, you would just say student is a subtype of person, right? Well, this is okay, but when you also say, okay, a student can also be an employee, what happens if the person should be an employee and a student at the same time? You have maybe two objects simultaneously that actually represent the same real-world object, which is weird. So role-oriented programming said, okay, we differentiate between natural type objects, which actually describe real things, and then we can define student as a role that this object can be assigned to. So there might be roles such as student, employee, and professor in this team of a chair at the university, and the person can be assigned to a student role or an employee role or a professor. And once again, Julia is quite nice for modeling all of this using a small DSL that I developed here. So what you can see here is that I define a new team called chair. This chair has some attributes, also like an ID attribute that I can use later to address this object. And some roles, of course, that have not only the name role, the role's name, like student, employee, and so on, but also the natural type that is allowed to play this role, like a person, and the allowed numbers of persons that are possibly playing this role. Like there's only one professor allowed, but multiple employees, for example. And of course, these roles can also have attributes. So you can model things like this with this macro. What happens then is that you would create a lot of structs, and again, add all of this in some database for managing all of this. For having really like a dynamic system in the end, you need to assign those roles and change them later. And you can see here how this is done in context.jl. Like you have this add assign rows macro where you say, okay, I assign rows to the chair object with the name chair of software technology at TU Dresden. I have 2 students, Julia and Romeo, which are assigned to these rows. I am then assigned to the employee role, and my professor gets also its role in this assignment. Later, you can then change those roles by disassigning this to the student role from the Romeo student and just add rows to a bunch of other students, for example. Those 2 macros would then also like check a lot of things, like are the multiplicities kept, are the natural types okay that you try to assign to the role, and so on. So this does a lot of checking of your underlying model here. And once again, I also thought this would be cool to combine with modeling toolkit. So here you can see basically a very similar thing as in the first plot. So you have a drone model in this case, where I define a lot of variables and equations for like the base case independently if the role has a role assigned or not. But there's also role-specific behavior, like which you can see here in this equation, and that is only valid if the role plays an observer role within an observation team. You will see on the next slide what this means then. What then happens is, like, if you simulate your system and again call a callback where you change the rows, you can reinitialize the equation system and then adapt the behavior according to these role distributions. And I did here a simulation based on a so-called K-coverage problem, which is all written with this role-based modeling and modeling toolkit. So you see these drones that are blue are uninteresting drones, and the red ones are looking for interesting objects. Now one got green, and as far as one of the drones detects the drone, it will automatically change its behavior in order to observe this object by flying around it and pointing the camera on it. Then it will automatically follow it here. Of course, you can do it multiple times because you can assign those rows to another observation team, which happened here. And of course, it also works the other way around. Like if one object gets uninteresting again, the team will be dissolved and they switch back to the default behavior. Okay, so to sum this up, context.jl allows context and role modeling for self-adaptive systems. So the context part is more or less about controlling, like let's say a monolithic system, while the role-based modeling is very nice for having swarm-like systems where a lot of interactions between objects happen. And I also wrote an integration with simulation infrastructure around modeling toolkit for that. And if you want to have a look, you can scan the QR code here, and then I'm happy to answer your questions.
Thank you so much. So we have a lot of time for questions. It would be just time for the 5-minute mark. Let's go to questions. Do you have any? Yeah.
So thanks very much. I was wondering about the context, because you gave example like temperature, which is a continuous variable, and how do you handle that in this framework?
So the context definition, of course, relies on discretizing this. So you would then define, for example, a state machine that observes the variable, the continuous variable, and then activates automatically these discrete classifications of the temperature. And of course, these thresholds have to be somehow estimated by the modeler also, yeah.
Very nice. Do we have another question before I do my question?
Yeah, maybe one on the debugging side. Let's say some error happens. I can probably easily see the function in which context the error occurs, but debugging why this context was activated, how easy is this, or did you find any issues with that?
Yeah, I mean, this can be complicated, like, but normally you have certain points in your program where you call this activate context function, so you can also kind of trace back where this activation came from. But yeah, I guess like extending some kind of debugger would be actually a nice thing in the future to do for that. Yeah.
So I have two questions. The first one is, it seems that you collect a lot of information that would be very nice to plot a kind of live. So as the simulation is running and it's going through the context, I would like to see that.
Mm-hmm.
Do you have some integrations with Mackie or plots that I can see, for example, that something transitions from sunny to...
No, I don't have yet. I mean, for some simulations I wrote this by myself, but I haven't like generalized that or so. But what you would have to do is basically every time you activate or deactivate something, you would somehow have to write this into, I don't know, a vector or whatever. And then, of course, you can return this as an object as well to the solution of the modeling toolkit simulation, basically. That wouldn't be a problem.
Okay. And my second question is, have you thought of integrating that with Dyad, since you're already on the MTK side?
I mean, as far as I know, Dyad isn't really like an open thing, so I guess it would
Since you're an academic, it's not too close either.
Yeah.
It's as close as it gets to open for a product.
Yeah. So I guess it would be not very simple for me without like getting really much in touch with all these Dyad people to add this.
No, I understand. Yeah.
But of course, yeah, like actually originally this project idea came from adding context to Modelica. And then I was saying, okay, I kind of like modeling toolkit more and it's also easier to use. And that's why I ended up with modeling toolkit. But of course, like at least in my opinion, we could add some value also to Dyad for this. I also had some talks with Mike Attila and so on about structural variability.
Yeah.
This is quite restricted right now. But yeah, if some of the Dyad people are here, I'm also happy to talk to them.
So that's why I asked.
Yeah.
Okay, that's great. Do we have any other questions in the audience? Let's squeeze our minds. Okay, maybe not.
Okay.
Thank you so much. Let's thank again our speaker.
Thanks.
behind it. And then at the very end, I have just one slide saying, we also have an implementation written in Julia. And today I will do the opposite. Okay, so I will just talk about the new stuff that we implemented in the last year in Sole. And if you're interested in any of the more theoretical stuff, just reach out, write me an email, or I'll be around for the whole day, so let's have a chat. Okay. As I was saying, today we will focus on two packages, on the Sole Logics package, and specifically on a new submodule that we implemented for many valued logics, and on the Sole Reasoners package, which is a new package built for doing a classical logical reasoning, but with a very niche family of logics, a very general family of logic. Okay. So let's begin with this new submodule. And first I have to say that from the literature, we know that we have a broad family of many valued logics. Okay. If you already heard the term fuzzy logics in the past, some of those, the one at the top, correspond to this kind of logic. So Gödel algebras, product algebras, and MV algebras correspond to Gödel logic, product logic, and Lukasiewicz logic. This taxonomy, as you may see, is for algebras. Why is that? Well, because we know that treating those kind of non-classical logics using their corresponding algebra is much simpler, and I will give you an example in a minute. The fact is that we don't want to restrict only to fuzzy logics, but also to have some logics where the order of the true values can also be partial. So we have true and false, like in classical logic, and then we have stuff in between. And some of this stuff can also be non-comparable. And so we have to take a very general structure. Don't worry about the definition. I just want to take a few points from it. Okay, but here's an FUW algebra. It's this kind of structure. We just have to know that we have some kind of lattice structure that can be used just to define the order between the values. Then we have an operation that we will use to treat the conjunction in the logic. And then we have a way of defining an implication such that we can define it in the same way for all the logics, for all the algebras that are in this family. Okay. The take-home message is that I have a partial order, I have a conjunction, and I can always derive the implication from the conjunction. So here are a few examples. These are some examples of lattice structures, of partial orders, and all of those are already implemented, and you can already use them with our framework, okay? And as you can see, there are some examples of partial orders, some examples of total orders, and some of those are actually correspond to different logics, because if I change the monoid operation, the conjunction, I can use the same order, but I change the way the values interact with each other, okay? Well, here I have some example of monoids, and specifically, again, if you are used to fuzzy logics, for example, you can implement the classical T-norms of fuzzy logics in this way using the monoid. So, for example, for Gödel logic, you will use the minimum between those values, so saying that A and B, where A and B are real values, is just taking the minimum between them. While if you use product logic, you take the product, the real product between those two numbers. And if you use the definition of implication from the previous slide, you can derive the implication for those logics in this way. Let's go to the other package. Because now we have our logic, we implemented many varied logics. We already supported temporal and spatial logics in SoleLogics.jl. Now what we did is combine them, so we can have both temporal and spatial kind of relation interpretation and a many-valued interpretation. And if you're not familiar with modal logics, which is the framework that we use to treat temporal and spatial logics, you can simply read these two operators are, it can be in the case that something happens. So let's say if that I take a point in time, I say that there must be at least one point in the future where something holds, while the box operator is read as it must be the case. So from now on, every time I have another point, it must happen that something. Of course, I'm not spending time talking about the semantics here, but you have to define the evaluation function for each of those operators, okay? And now, once you have that, you can do the SAT, the classical SAT problem that you have in computer science. But since now we are talking about many valued logics, we can also generalize this kind of notion. We can say that a formula is alpha satisfied by some model, by some interpretation, if its valuation is at least a value alpha. And then we say that the alpha satisfiable problem is finding if there is such a model for a formula, and validity is simply for every model, for any interpretation, that formula is always at least alpha satisfied. How can we solve with this kind of problem? We use something called an analytic tableau, which looks something like this, okay? Again, I won't go into the details, but this is simply a dynamic tree structure, okay? We never want, hopefully, to build the whole tree because computation-wise, that's gonna be expensive, okay? But what we are trying to do is trying to find a model which is an example of the satisfiability of my formula, or if I'm checking if that formula is always valid, it is a tautology, I have to check that if I negate that formula, then I can never find a counterexample. If I find one, I can also have a look at the counterexample. And so here, each node of this tree reads as, it is true that my formula has at least a value alpha, or it is false that blah, 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 or vice versa. And each branch corresponds to a specific valuation in a specific scenario, okay? We are trying to build up both a temporal or spatial scenario and evaluation of my proposition, okay? And I'm trying to find one that satisfies my formula. And I can see that for this very simple formula, I have alpha satisfiability using a Gödel logic with 3 values. I have 0, 1/2, and 1. And I take as a conjunction the minimum between 2 values. And it's easy to find. I just have to take one of those branches, and that's a model for my formula. While if I change the t-norm, if I use Lukasiewicz t-norm, that is not the case. I see that for any combination, I always get a closed branch, okay? Now I have a very simple live demo that we can have a look at. Let's just first import our packages. And as you can see, those packages are very light. I can do that fairly easily. So I'm importing Solid logics, the submodule many valued logics, and the Solid reasoner package. Then, since here I didn't state that I'm using some very simple modal logic, now I want to use a temporal modal logic. I define the future relation. This reads as, I have points in time, and I want to check if a point is in the future with respect to another. And I will bound that with a diamond operator, as I was talking about in a few slides ago. Then I also import from many valued logics my Gödel logic with 3 values, my Lukasiewicz logic with 3 values, and some value alpha between 0 and 1. And I define a proposition, an atom, to define my formula. I bound my relation to a diamond operator, so now I have this diamond operator which states there is at least a point in the future where something is true. And I build my formula with this line. See, the same formula I have in my slides up there. Okay, so I'm checking diamond of future, P and alpha, okay? And now I will call my Tableau system. I'm using the Tableau for many valued linear temporal logic with future and past. You can check the documentation for that, but we have different tableaus, okay, for the different kind of logics. And if I ask if phi is at least alpha in G3, it's gonna take a few seconds, but it's gonna build the Tableau system, and it's gonna find a model, okay? While if I do the same for Lukasiewicz, I cannot find one. And that's fairly easy to see, because here I can just take alpha as value of p. If I take the minimum between the 2 values, I get alpha. I say, in the future, alpha, which is alpha and alpha is alpha, so great, very simple model. Here I can never do that, because if, for example, I do this such that here in the middle I have 1, for example, I take p equal 1. 1 and alpha is 1 plus alpha minus 1, so it is alpha. Just think as alpha as a half here, okay, in this example. And then I state this in the future alpha, okay. Alpha and alpha, well, alpha and alpha is half plus half minus 1, which is 0. So it's false. That's why this is never satisfiable. Concluding, of course there are limitations. There are many limitations in this work, okay? The first one is that I only shown you finite structures, okay? While most of the time you're interested in fuzzy logics or very simple structures. So this is because we wanted to start from the very general approach, okay? And then trying to optimize each single case. That's why now we are working on a different reasoning system specialized for continuous chains, so for fuzzy logics. And we're also thinking about reasoning tools for specific much easier logics where we can do much more optimization because, of course, I only showed the simple example, but if you go with others, that's going to be problematic. And then we also want to think about model checking and advanced techniques for model checking, since the ones we have at the moment are just the naive ones. With that, I thank you very much for the attention and ask if there are any questions.
Thank you very much. We have some time for questions, so who would like to go? I find that the hard mathematical problems are also very hard to ask something for. But we do have some time. If you can prepare for your next talk in the meantime.
You can also ask, is this useful or not?
Well, Gauss didn't think his stuff was useful until it was. So, you know, it's too soon to answer this question. That's
yeah, I know.
Yeah.
So, thanks very much, because I did see some of the past Sole presentation from your group, and I was wondering how does this work integrate with the rest of the things you have been doing?
Okay, thank you so much for the question. So if some attended the last few JuliaCons may remember, or if not, I will tell you now, that one of the main reasons for building this package was to generalize, to try to enhance some very classical machine learning algorithms, like decision trees, for example, which are bounded only to propositional logic in most of the cases. And we tried extending them to modal logic to work with temporal and spatial logics, okay? And that was successful. Now, what we wanted to try was doing the same also with many valued logics, okay? There is some work from the past with fuzzy logics, and we also wanted to extend that with partial orders. And of course, when I started my PhD, we were like, sure, most of this stuff does already exist in mathematics, and that was not the case, so we had to implement these foundations for that. But the main reason is that, because at some point we want to build classical machine learning algorithms, okay, using this kind of logics. That's the main aim. We are far from that, but
that's fine. Okay, thank you very much. Do we have another question? We have 1 minute. Okay, if there is no question, let's move on to set you up for the next talk.
Yes.
So our next speaker is Tobias Thumerer. I hope I said that correctly. Big simulation models suddenly feel very small with fmi.jl. The floor is yours.
Yeah, thank you. My name is Tobias Thumerer. The title of my talk is Big Simulation Models Suddenly Feel Very Small with fmi.jl. And it's basically a talk about a software library. And what is interesting is that the first release of this library was like a little more than 5 years ago, and the library was already part of 2 workshops here at JuliaCon, so in 2023 and 2024, but I never gave a talk about FMI.jl. And yeah, I'm currently on parent leave, and I was looking for a way to attend my very favorite conference, so finally, after 5 years now, I'm giving a talk about FMI.jl. And because it's a lot about programming, I'm throwing some interesting code snippets at you, and we'll show you how to handle, how easy it is to handle very big simulation models in Julia. So FMI, what is even that? So don't upset the FMI folks, use your abbreviations correctly. So FMI is the functional mockup interface, so it's an industry standard for exchange and co-simulation of large simulation models, and there are over 280 tools supporting it, including the Julia programming language. And to keep it short, it's the industry standard for the exchange of simulation models. On the other hand, there's the FMU, so the functional mockup unit, and the FMU is a simulation model that implements the FMI. So technically, it's a zip archive containing an XML model description and platform-specific binaries. So to summarize this, your tool supports FMI, but if you can share it with your coworker, then it's most certainly an FMU. So what can we do with these FMUs in Julia? So before we can do anything, we need to load the FMU, and this is super easy 4 steps. So we are just loading in fmi.jl. Then we load the FMU by specifying the source path. Then we can have some fun with the FMU, and after everything's done, we need to unload the FMU because it's an externally linked binary, so it's not part of Julia garbage collection, so we need to release it by hand. So if you prefer this file I/O syntax style coding, then you can also do it like this. In the second example, the unload function is automatically called before we are leaving the local scope. Yeah, the fun part is, of course, that do something here in between. So yeah, it's about simulation, so let's simulate a little. And here again, we have 2 different options. So the first one is co-simulation. So co-simulation means the FMUs ship together with an ODE or DAE solver. So this is the first option. The second option is model exchange, so abbreviated by ME. And in this scenario, the solver is not part of the FMU, so we need to specify a solver by hand, or we use the auto-select feature of differential equations by loading this one in, and it will pick a proper solver automatically. So many simulation parameters have default values like the time interval that I want to simulate, the default parameterization for my model. And if we want to change something, we have a variety of keywords available, and some of them are introduced here in the following slides. So one of the most important is record values. So that allows us to specify a vector of values that we're interested in. So we can simply use the string identifiers that we used in the original modeling environment, and after the export of the FMU, and after simulation, we find the following. So this is the results object containing lots of things, but the interesting part, of course, is the values that we specified to be recorded here on the right. So this becomes easier to handle if we just plot it, of course. So let's load the plotting library plots. And this way, the plot command is automatically extended to being able to plot FMU simulation results, including, for example, a proper legend here on the top left. So next, often we want to change the time interval of the simulation. So this is done via the keyword tspan. So you might also know from Simulbase, for example. And by specifying this longer time span, we can, of course, find a longer plot as well here on the right. So, and if we now switch from co-simulation to model exchange, we can also specify solvers from differential equations like the tsit5 here in this example. So we are loading in ordinary difficult tsit5, and then we can manually set the solver we want the FMU to be solved with. So there are many, many more keywords, so just have a look in the API if you're interested. So what else can we do? We can do linearization or differentiation in general. So if we don't want to run a simulation but evaluate the FMU for a single point in space-time, we can just call the FMU instance like a function. And everything is fully differentiable here as long as we load in FMI sensitivity. So, for example, we can use forward diff, and we can get, in this example, the derivative of the right-hand side with respect to the state, so the matrix A in systems and control theory. Or we switch to using reverse diff, and this way we can get the derivative of the output with respect to the state, which is the matrix C in systems and control theory. And of course, both AD frameworks work for both cases. And yeah, these calls again have a variety of optional keywords. So you can, for example, set inputs, you can set states, you can set time, you can obtain outputs, derivatives, event indicators, and more. And if you feel like you need more speed, then Valentin Höpfner here gave a beautiful talk on how to make differentiation of FMUs working together with Enzyme for maximum speed. It's already over, so I think it was like an hour ago or something, but you can find it on YouTube soon for sure. So next fun idea is if FMUs are now fully differentiable and compliant with automatic differentiation, we can use them as part of artificial neural networks or machine learning in general. So we can set up a neural network chain as we know it, but now we evaluate an FMU inside this chain here. So this way we have some neurons that are able to correct the state, then the state is passed into the FMU, the state derivative is returned, and we have two additional layers that are able to correct the dynamics of the system. And this structure we called neural FMUs back then, and these are a very nice way to introduce unmodeled physical effects to an already compiled FMU. So if this is interesting for you, there are these two JuliaCon workshops in 2023 and 2024 where you can find video records of. So now that we talked a lot about how to get FMUs into Julia, it's a good point to say that we can also do it the other way around. So we can compile Julia code into an FMU that can be run in a simulation tool that has support for FMI. So this is very simple as well. So first we specify a constructor here. So this is code that runs as soon as the FMU is loaded. And here we create a FMU and override all the functions we're interested in. For example, the function is called when outputs are required. And we can further specify and introduce variables that are visible for the FMI simulation tool later. And there's also a second option. If we require full access to all the FMI functions, so the FMI interface is quite complex. We can override all the FMI functions that we are interested in with Julia functions by our own. And which way to take basically depends on your use case. So this one is a simple interface. This one is like the freedom of options. And yeah, independent of the way we take, we can then just do a safe FMU that compiles everything in a standard compliant FMU. And finally, you can get creative. So there's also an interface to set up an FMU simulation just like an ODE problem in SciML base, also with support for common functions and keywords. So for example, we have a function remake, a function solve. In this way, you can, in theory, stick FMUs to everything that is compliant with Julia differential equations. And this is quite a cool feature, I think. So, to conclude, FMI hides complexity of simulation models in terms of model size, but also in terms of interfaces. In this way, it provides, in my opinion, a very clever solution to handle huge simulation models as they are used in industry, but also in academia. And you can do a lot of funny things, as we showed here, so independent of if the model consists of 10 or 10,000 equations. FMI and FMI.jl let you almost forget that the model you're working with is really that big. And if you find this useful and want to support, you can start it on GitHub or make a pull request. Contributors are always welcome. And that said, thank you very much for your attention, and I'm open for questions now.
Let's thank our user. Thank you so much. That was a great talk, actually. I love FMIs. Do you have questions in the audience? Amazing.
So, thank you for the talk and for your work on the suite of packages. My question is, so I think FMI version 3 introduced the adjoint sensitivity functionality as well. So is your library aware of the directional derivative and adjoint derivative APIs, and does it take advantage of them when you are like solving the system?
Yes, that's an excellent question. So of course we know this get adjoint feature, and we are happy that it is there. So because it drastically improves the performance of reverse mode automatic differentiation, because we are not required to get the entire Jacobian. We can just multiply with it. This is of course a huge speed up. So there are two sides of this coin. So so we are aware of this feature, and it's not yet fully implemented in the entire ecosystem, but at some places we are already actively using it. The other side is that unfortunately this adjoint derivative feature is not yet supported by that many other tools. So if we want to make, so it's an optional feature in FMI actually, so like the directional derivatives as well. So it's not, the number of tools that implement it is very, very, very low. I would say so I know one, I know a single one actually that did it, and that's why there's limited use of it for now. But as soon as we will get more tools implementing it, we will use it, of course, the entire ecosystem. Yeah.
That sounds great. And Julia is always ahead of the curve, so
yeah,
we'll get there.
Yeah.
Do we have other questions? I have one. So do you have any ideas about using WASM-based FMIs for Julia?
FMUs based?
Why on WASM, like the WebAssembly stuff? It's not standard yet, but it's very cool.
Yeah, I need to admit that I'm not aware of WASM.
Okay, that's fine. It's a web technology that it's basically a compilation target for. It's like assembly, but for the web. But it's very safe. If that is useful for some use cases, not most. It's fine not to know it.
Okay.
Okay. Do we have any other questions? If so, we can thank our users again. Our speaker again. I keep saying you. Thank you very much, Tobias. So for the next session, our speaker is Rainer Heinzmann. I hope I said that correctly. And we're going to hear him talk about structured illumination microscopy, JL.
Yes. Okay, yeah. Welcome, everybody. So once this is set up, yeah. So structured illumination microscopy is a a mode of light microscopy where you get super resolution, about a factor of 2 over the standard resolution of a microscope. And I want to start with a very quick introduction what this method is, and then, of course, the main point of the talk is to go into the details of how this is implemented in this particular case. I need these ones. Okay. There you go. So the principle is maybe easiest seen if I show you this. So I don't know if you can see these slides here. Works a bit better if there's a bright background. But the point is that you can see nothing because it's too detailed. It's beyond your resolution capability. And I have here another slide which has a very, very fine grating printed on it. And if I put these two slides together, then something funny happens, and maybe you can realize that there's something visible. I don't know, can you see that? It's a person, yeah. It's actually Ernst Abbe, who is kind of famous in Jena. Right, so the point, the takeaway message here is that high resolution times high resolution gives you, beyond other things, low resolution. And that's kind of cool because you can use that as encoding in your microscope, the high resolution information. So we are actually not interested in that image here. We are interested in the details of what is in here. And we use an encoding grid to code it down to low frequencies, which a microscope can image. So mathematically, what does that mean? Well, we are doing fluorescence microscopy, so the emitted intensity is a product of the object density with the illumination intensity. And you can now translate that statement to Fourier space, where the convolution theorem comes in, and so the Fourier transform is indicated by the little tilde over the object and the excitation intensity. So graphically, what does that mean? Well, the object, we have no idea what it is. That's what we want to find out. But the illumination intensity, we have very good control over. So what we do is we illuminate with a standing wave pattern that is as fine as possible. And this standing wave pattern is actually a cosine square, which you can write as a constant plus a cosine of the double frequency. And if you Fourier transform that, you get these three peaks. The cosine gives you e to the ikx, e to the minus ikx, and the delta in the middle is from the constant. So now we have to convolve our object with that thing. What does that mean? We have to put the object in all three locations, like this, and basically what we would have as an emitted intensity in the sample is the simple sum of these three things. Now, the microscope will actually modify that and will apply a transfer function, which is basically the Fourier transform of the point spread function. So this is where the incoherent nature of fluorescence is very important. There's no interference between neighboring fluorophores. Good, so that's roughly the data we have. So what we now do is we want to sort of invert that whole process. So how do you do that? Well, you acquire 3 images instead of 1 image of this shape. And why is that important? Well, these peaks vary. This peak here has a complex phase phi, so e to the I phi, and this e to the I minus phi, this is simply the Fourier shift theorem. If you're shifting the grating in one space, you get this rotation. And that's cool. That's 3 independent sort of modifications. We have 3 unknowns, so we can invert that equation system. That's exactly what you do. You're taking 3 images and apply an inverse of this equation system. And so in a nutshell, you first correct for the effect of the optical transfer function, then you're applying this inverse to extract these 3 components, then you leave the center one in the middle, then you shift the one from the right side to the middle because its object frequency should be living there, and the other way around from the left side to the right. And then you do a weighted averaging. That is kind of important because the quality after this first step is infinitely bad at the edges here, because there's noise everywhere, and dividing by something close to 0 magnifies the noise. But in the middle, you would average, and here this one goes bad, so you see it's a frequency weighted average. And the final step, you need to take care of that this would still be infinitely bad, so you're suppressing that with something that's called apodization, so you're multiplying it with a final function. Right, and so this is basically what is implemented in the SIM toolbox, structural illumination, and that by itself is not very exciting. I would say it's an old, well-known method. The question is only how do you implement that efficiently? And so this sort of toolbox
has a few special things that I want to point out. So first thing, it is actually separating the reconstruction into two parts, which is more practical reason. One is to prepare all the data structures, allocate all the memory, because that's supposedly only run once, and then in a loop, you're running the actual reconstruction maybe multiple times. For example, for every slice of a volume, if you want to do it slice-wise rather than in 3D, or for actually every time step of a whole movie of how the cell is moving along or something like this. And well, then yeah, there's a structure for the reconstruction parameters, which is mostly due to the fact that this is a very large amount of parameters that you can set, all kinds of algorithmic details that you can set, and at some point it becomes annoying if you have like a function call with a, whatever, 50 parameters. So that's why they're all put together into one structure. Right, then something that I didn't and will not go much into is how do you estimate the parameters, because it turns out in practice you don't know exactly what is the grading constant, all these things. So you have to have cross correlations that find that out, and that's also in the toolbox. And so if you're done with that, you basically get this SIM parameter structure here labeled SP, in which all of this is gobbled up. And the interesting part there is it is constructed in such a way that it can handle all kinds of different structured illumination modes. So there's different ways you can do that. You can do this with gratings like this, or you can do this with two-dimensional dot-like gratings. And what do they have in common? Well, they have in common that they all consist of a number of k peaks. So even the two-dimensional structure gives you k vector peaks. So in k space, in Fourier space, you have these peaks. And so it is straightforward to then say, okay, let's just say in general there's a list of these vectors, and then every image defines exactly which phase of which vector and which strength of which vector is present. And then the whole thing is a slightly bigger equation system that you're solving. And this is how this is done. So the classical, or let's say slightly advanced pipeline of sim reconstruction works like this. You have a raw stack with, for example, 5 directions, 5 phase images. You estimate the parameters, then you unmix these orders with the inverse of the mixing matrix. And then comes the nasty bit that's called the upsampling. Later on, you saw we have to shift in Fourier space. However, the raw data is sampled according to the Nyquist limit in real space. So we don't have enough space to shift stuff around. We would get aliasing. So you need to make space, and that is super expensive. You need to Fourier transform your data. You need to add zeros and come back to real space, because that's where you do the shifting by multiplication with e to the ikx. And so this is the bottleneck of the whole algorithm that makes it slow, classically. And then, yeah, you apply the shift, and finally you apply your final Wiener filter or iterative reconstruction. So what is now new in the reconstruction is to identify that this is the bad part, and can we somehow avoid it? And the way to avoid it is by separating the shifting into 2 steps. It sounds strange, we do 2 shifts instead of 1, but the trick is we shift by subpixels, which has no aliasing problem, first in real space of the raw data. Then we've done the subpixel part, and once we are in Fourier space, we can do the full pixels quite easily, because that's just the integer part, and that means like a stamp to press your Fourier transformed results somewhere into the result image, and that we can then accumulate in Fourier space. And that makes it very, very fast. So then you do all these other things, the weighted averaging and so on, and the final Wiener filter. So I have to speed up a little bit in interest of time. So I cannot go too much into the details, but yeah, one thing, there was another toolbox I talked earlier about, it's called separable functions, and that we make use of in this toolbox as well, because it allows you to apply this e to the ikx quite efficiently, because you can separate it into an x and a y component, and you can use Julia's broadcasting mechanism to apply that in every pixel without having to calculate it e to the ikx in every pixel, which would make it slow. And then another trick is that you can actually work in what I call RFFT space, so that's exactly basically the half complex plane, and you can directly press all your stencils into this half-complex plane if you do it right. And that, interestingly, still means you have to apply the positive and negative ones, so you have to sort of reflect this one. You do only one Fourier transform, but then you take the complex conjugate flipped version, and this might still have some overlap, and you have to also put it into this position.
right? So it still saves you a lot of Fourier transform this way. And yeah, then another thing is to make the memory layout such that there's no dynamic allocation, so then you can run it essentially allocation-free after the large bit of initial allocations. Good. This is some comparisons. So you see, for example, in CUDA, we could get a pretty big speed up for three-dimensional data sets like this. And I want to end with some results. So here you see a classical wide field image that Paolo Meran and Hornan Wang in my lab have acquired last week. And this is just essentially how a normal microscope image would look like of these fibers. And that's actually a small part of these huge images, 2048 by 2048, but you wouldn't appreciate the details. So that's why I zoomed in here. And then if you do a Wiener filtered structural illumination reconstruction, you can probably see quite nicely here the resolution improvement. And then you can also replace the last Wiener filtering step with an iterative maximum likelihood deconvolution step, and then you get sort of this result. Okay, and with that, I want to end my talk. I would like to thank Felix Wechsler and, of course, Paolo and Horan for their contributions. And yeah, there's always stuff to do. It's available. It's not a released package, but you can, of course, install it and try it out yourself if you like. And thank you very much for listening.
Let's thank our speaker. So before I ask for questions, can you use that in satellite data? Can you use this methodology?
Well, so there's something related in satellite which they call SAR, synthetic aperture radar, okay. But that is a coherent technique. So there are a lot of similarities, but there are also some differences. The biggest difference, this is an incoherent method. So I'm talking intensity times intensity gives intensity, whereas in SAR, this is radar data which is coherent, basically.
Okay. Are there any other questions from the audience? We have.
So I guess in your pipeline, I'm just wondering what are the parameters that you have remaining now with your optimized pipeline?
Sorry, whether the parameters are...
I'm just wondering, what are the parameters in their pipeline?
The unknown parameters that I have to figure out before starting the real reconstruction. So the most important one is a very precise estimate of this K vector position. So if you get that wrong by, let's say, 1 pixel, that already means a phase mismatch, 100% wrong reconstruction in half of your image. Right, so you can appreciate you need that at least better than 0.1 pixel K-space estimate. That's the most difficult thing because you need to iteratively obtain that parameter. Then the next important one is the individual phases of all the images. That can vary. It can also vary because you start to bleach structure into your sample that you want to compensate in the reconstruction. So these are the most important. And the one parameter that I still don't have a good handle how to estimate is the contrast of the K vectors. So this one, we have routines for estimating it, but in the end I throw the data away and put some theoretical values in because the reconstruction looks nicer that way. And that's ongoing work, so to say. And I think that's the most important part. The rest, I mean, you know what the laser wavelength is, you know what the NA of your objective is. You can measure a point spread function. That's a little bit better to use a measured point spread function as opposed to a theoretical one, but it's not critical.
Okay, thank you so much. Do we have other questions? We do have 1 minute. And the speaker of the next talk should be preparing. Is the speaker here?
Oh, then we have lots of time now.
Okay, then we can ask away.
No pressure. Oh, okay. You can actually see a second person in here. I didn't show that, but if I rotate it, instead of Ernst Abbe, you get another person here. Can you see that? I should jump up higher. Let's see. There's a trick. I don't know if you can see this. Yeah, whatever. You can come down and see yourself if you want. So you can try to guess who's that second person in there.
Yeah,
Yeah.
we do. You can come over.
Yeah, they don't fit.
Yeah. Rainer, one more question. So I was wondering, what does the accelerated pipeline buy you? Why does it matter that this is faster?
Well, if you are a biologist working at a microscope, and you're acquiring, let's say, an hour of data, you would like to see live the super resolution bits, because let's say you're interested in a particular fusion of two vesicles or something like this, and if you can't see it live, then you cannot interact with the microscope. If you see, oh, that was unsuccessful, you want to stop your experiment and maybe look somewhere else for another fusion or something like this, right? So, and that's why a certain reconstruction speed is important. And if you know, there's a company in China, which I think a big part of their success is also due to that they have a really fast reconstruction pipeline as well, with big GPUs, and that allows nice lifestyle viewing in super resolution mode.
Okay. Any other questions before we go? Okay, thank you so much. That was really
Thank
interesting.
you.
Da in Berndeutsch wird immer alles abgekürzt.
1 minute, 1 minute. Are you all right? Ah, no, I don't have one. The keyboard work for moving on? Okay.
But the mouse, that's the, I wanted to, because on other ones it showed me the mouse then as well, but now not. Okay, nice.
Okay, so for our next talk, Yera will take us through the Go Meta. This is the Meta line announcement, the release of Go Meta. Yera, the floor is yours.
Okay. Hello. Oh, I can hear myself very well here. Yes, well, the release of Go Meta was just yesterday or the day before. There's still a lots of flaws in it. There's a website with it now, which needs still a lot of work. So I wrote a little attention or be careful thing. So there will be improvements on that one. Right, here you can find that website. So let's have a look. So what is it actually? The key thing you need to remember, it is all about embedding formalized meaning into comments, all kinds of comments. And that's the difference. So you can actually embed it into Julia files, naturally. Rust, LaTeX, maybe Word documents. I'm working on that at the moment. It does work, some things. As you can see here, you can see what's implemented. It's, yeah, the Word document, that's still experimental. So in general, Go Meta, it's a domain-specific language, but it's more than that. It's actually a whole framework, because you need to abstract the metadata out of all the different files, work with it, pass it on to the extensions, because Go Meta does actually not, it only evaluates what should be happening, but it doesn't actually act on it. So here we have the absorb and evaluates that metadata, pass it on to the extensions. And the extensions, that is still something, there still needs to be a lot of different extensions to be written, but that's exactly the idea. Go Meta, the framework, provides the ground for these kind of things. At the moment, the extensions are more toy examples. Now, before it actually can absorb the metadata, it needs to read in the file and see exactly where the metadata is and how it is in relation to the other ones, because there's a hierarchy, like which metadata inherits from which other one. So what we have here are the BLS is a module. It reads in the file into blocks, lines, segments. There's actually also files. There are other levels as well, and it might expand later on that one. These are all different BLS components. These BLS components, they can have different flavors, such as meta, of course. Here you see meta, text, code. Later on, maybe other flavors will come. code, or in text, there's a difference between Markdown and other text, but all these kind of things you can still build on or extend later on. Here is just a toy tool I use to see then how it actually reading it in, because it reads it into a BLS component tree structure. Just is a bit enlarged. So here you can see the bottoms of the line 7 and 8. So you have a block of code. It contains 2 lines of code. The first one, another 2 segments of code. And then the last segment down there, in the last line, is a meta line. You can see that over there. So, or maybe I did not mention that beforehand, but obviously the twiggles there, that sign, that kicks off a meta line, segment, or whatever. Now here you see the same thing works with C, and the same thing works with LaTeX. That's implemented, that works. Of course, it's all still a bit rough around the edges, but it's proven that it works. So apart from just reading in that tree structure, actually it reads a lot more than that, because it needs to actually see, is that component attached to the metadata or not? Where does it inherit from? What kind of text is it? Is it a markdown? Is it an empty string? All these kind of things. I can't go into details. There's a lot more that actually is in each component. So why actually use the meta or Go meta, the metadata? Well, there's these examples here are just like literate is. So you can have one source file and produce actually a lot of different outputs. So you can make websites with it, PDFs, Jupyter notebooks, Documenter. But this is all then through extensions. The extensions, they act actually on what the Go Meta framework evaluates. I do have, that's the next slide, for instance here, this is a Jupyter notebook then, with the one there is hidden. Why is it hidden? Because of some metadata thing there. So the notebook, Jupyter notebook, already works. This is then actually the JSON file you see here. Why do I show that? Well, it does not show in the Jupyter notebook itself when it's hidden, but it is actually in the JSON file, as you can see here, that one. That's the difference between, discard and throw out, or just hide it away. Here we have something with Documenter, where you also have, well, up there you see, for instance, the hide. The hide, it's an instance of an alterand. An alterand, that's a Go meta type. And the curly brackets behind each alterand, that's the condition under which it applies. So if something has a beer on it, for instance, like the thing down there, then the hide is going to apply. Well, I go a bit faster. The whole thing, context, is actually very relevant, especially also today with the AI. It's not just us using context. The AIs can work a lot better if they have context. Now, if you actually have tons of files, and you actually interlink the different parts within the files, so it's not just interlinking files, it's the different parts that know where other parts are in other files. And if you can say, okay, this is my context, not the files. I have one snippet there, that's your context, let's go. That works better for us, it works better for the AIs. So how does it actually work? Yes, well, this is the input file. This is a first-degree output file. I say first degree because that's not the rendered stuff, right? Sometimes you have, like with the JSON files, and then you only render. So here it does make no difference. Why not? Because there I had a bang beforehand, and a bang is don't run that metadata. the cherry things, they do actually apply. But because it's actually not an action, you don't see it. So the cherries do apply when it is code and contains meta, or is meta. But you don't see an action here. You see the action now, because now the hide actually can act, and it acts when it's cherry or that note thing there. And where does it do that? It does with the metadata. Why? Because they have a label cherry on them, right? Why do they have it on there? Because there is meta. So let's have another look. Exactly. So here we have now a label over there, and now it also applies to the whole text. Because now the whole text here has that label, it inherits from the metadata, it is attached to it. If the line is right attached to a meta block, then it inherits that. And then it gets hidden because nodes get hidden. This one here, line 7, is now, before it was hidden, now it's not anymore. Why does it now not apply anymore to that one? Well, within the text, if you have a space between the text, it's not going to start your new meta block, because it's natural that you have empty lines in a meta block or in a text thing. But if it starts a new type, then it is a new block. And that block is not attached to the other one, so it's not attached to the meta where the node is, so it is not hidden. You see also the twos here behind the twiggle and then the 1. It goes hierarchically. You inherit that way here. The 1 is not going to inherit here anymore because it is a new, it's not a subsection anymore. Subsections inherit. It's a hierarchy. The other ones don't. So this one here kind of skips out of that subsection again. Yeah. There is, I used Claude at the end heavily because, well, I didn't think it actually would work. I did everything, the whole concept, everything was up till April done without anything. I didn't even know what Claude was. I read it sometimes. And I have to say, it took me so unbelievably long to implement. So the baby things all worked, but then to start doing the tests, so there are like 800 tests on it now, and that's just the public version. The private version is around 10,000 tests, because there's so many different things that can go wrong, and that's also why I have difficulties. I mean, it takes me longer, for instance, the label Alterand. I want to add new labels to it. At the moment, you have a fixed number of labels. But if you allow that you can add different, users can add different labels as they want, then it becomes very dangerous, because if you use the code of someone else, someone can splice in dangerous code. So I need to really see what you actually can, which labels that you actually then can splice in yourself, and what can you pass on, and there's certain opt-in things as well. I used to use the Julia parser for certain things, and by now I use my own parser out of security things, and the Julia is an opt-in, and then you have full access to the whole Julia parser within these conditional things, so you can splice in whole functions. And then, of course, it becomes dangerous if you don't know the code of someone else. Yes. And that's my last.
Okay, thank you very much. Let's thank our speaker.
Sorry, it was very dense, but I just wanted to pass it all on.
Yeah, that's fine. Thank you very much. We have some time for questions, and then it's the lunch break. So who wants to ask?
are you using this yourself for some sort of other code project? And if so, how are you using it?
Actually, so the Julia you see, or the Go meta that you see publicly, is not the Go meta I have on my own working. Because I go, let's go public, and it takes everything else out. It takes my comments out, it takes all possible certain, and I can really say what I want to go in certain files and whatnot. And I don't have to do that in single lines. I can just go somewhere in a config file, and it goes over all the files. So if I have, it must have this and that condition to go public, then it goes public. I mean, if I have, for instance, a private label, or it's then up to you how you set it up, but these are the options that you have, right? And of course, I don't share then my metadata is also not in it. I just go like, well, discard metadata, it filters that whole stuff out automatically.
No, I guess I meant more, how do you use this metadata practically? Like, what do you use it for? Like,
well, that was an example.
Okay.
Because they have labels on them, my code, so I can say, well, make that in the public repo, but not the other things, for instance. And that is what I do. Yeah. So and all my little toy examples and my stupid little tests and whatever, you know, like they hopefully should not be in the public release. Yeah.
Yeah, that makes sense. It's like a preprocessor for the project.
Yeah, but I mean, it's not just for. I use the hide and discard because I can visually show it.
Okay.
But you have all kinds of, so these are, hide is, there's an alterand, it's like, alterands are like the types of Go meta, and that is one that works. Then the label is a type that works, but you can make many, many different types, which have completely different functions associated with them. They have different, different purposes, different things. And you can, the idea is that you can actually just add that in yourself, write a little type yourself, just as you do in another language. You make your own little thing, and then you build it into the Go meta framework. It will evaluate through just as it does here with the hierarchies and the whole where do you what apply. It evaluates, passes it on to a certain extension, and the extension, I mean, what can it be? I mean, what do you do with metadata at the end, or data in general? It can be all kinds of extensions. It's just any function then at the end.
Okay.
Yeah.
Lunch is waiting. Thank you so much again. Let's thank our speaker. So that was it for this session. Right next up, we have the break, 1 hour and a half. Thank you very much for being here.
Hello? Alrighty, we'll go ahead and get started with our session here, our first 15-minute talk. As a reminder, when we start questions, if I can have the next speaker go ahead and come down so they can get set up with their mic and get set up with their laptop and their slides. So with that, I'll hand it over to Satoshi for his talk on running Julia everywhere from mobile to web.
Okay. Let's try. This is my family Goma-chan, and this is Goma-chan projector into two-dimensional space. So, yeah, the joke is over. And I'm an independent software engineer working around the Julia ecosystem, and recently I'm interested in Rust. Today I'm introduce my personal project, Subset Julia VMs, also S-Julia for short. This is why I created. This is a stack-based Julia virtual machine that accepts Julia style code. It looks like Julia and works like Python. I mean, a little slow, but a little faster than Python. I mean, this cartoon explains all of them. If the Goma-chan throws a code, something like println hello, then the virtual machine outputs hello. So since our virtual machine is written in Rust, so for example, we can distribute the Julia iOS into iOS Android devices and web browser, where the standard Julia runtime is difficult to use. Yes, and there are three results you can enjoy. Just scan it. First, there is iOS store application that is available on Apple Store. You can enjoy some easy code, and you can also enjoy visualization, and you can also enjoy REPL feature. And to prove I'm not cheating at all, I disclose source code named Julia VM OSS. You can try for free if you have a Rust environment. Installing Rust is so easy, so just Google it. And you may note that this application, iOS application, is not free, paid application. So you may want to try my result for free. So I prepared a Subset Julia web ground. And let's run the code. Yes, hello, what happens? Okay, it's cool. Okay, you only have to remember just Subset Julia VMs. Please Google it later. And the thing is, we believing next slide with the very same virtual machine. Yes, every programming learning journey starts with hello world. Let's run this. Yes, it works. To prove I'm not cheating at all, let's execute code something like using plot sine function. Yes, it works. Plot, bang, cosine function also works. Yes, and the title, title. Hi from JuliaCon 2026 in Japanese. Oh, sorry. Title. Oh my God. Okay. Okay, it works. Yeah. Thank you. Yes, and next slide, I prepared a more complicated example. So you can try interactive plots distribution random. I prepared an example. I have fractal visualization. Let's run this. Yes, it displays, you can try Felon, Sierpinski, and Dragon example. So as you can see, this is a macro. You can use manipulate macro in my product. Yes. Yes, and demo is over. Let me walk through why I created it. Because about 10 years ago, I loved Python stuff. Python is an iOS application that run Python on iPad. So I want to try same way. I'm wondering, can I run Julia on my iPad? Yes, this is my second question, but some people ask me, especially teachers who teach math, also, can I use Julia on iPad? I want to try. Okay, let me solve the problem. Yes, you may be wondering, it is easy to use for Julia from mobile devices because there is another service, cloud-based application. But there is a drawback. So CPU, the resource is not rich. So we should prepare 60 minutes to try out ordinary differential equations. This is much bigger than my talk. Yes, this is a natural question. It is natural to build Julia from scratch. Yes, it is natural, but there is a technical barriers. As you know, official Julia relies on JIT compilations as just in time, but iOS restrict the JIT compilation. So which means ordinary iOS application cannot freely regenerate and execute code at runtime, which we call WXOR execution policy. And also, Apple Store rules also download code that changes application functionality. So which means we cannot install a JL package. So it's not difficult, I think. So, but however, my project, Subset Julia VMS, uses a bundled interpreter instead, and Julia code is compiled into how to say bytecode. This is just a vector of instructions. But 3 weeks ago, I came up idea. Can I put Apple Julia into iOS? So I asked Codex. So it works. ChatGPT answers my question. Interestingly, there is an option dash compare in the official Julia. So if we set the comparison is no, so it technically disables the comparison. So therefore, the following the 5 code works technically, yes. But however, the matrix and vector multiplication does not work because this is internally we call a C call function, which requires compile enable. We should enable the compile option. So I don't think it is very trivial that we cannot linear algebra functionality. And what is worse, this is very slow compared to my subset Java application. So you should use my application instead. So how can I write subject Julian VM? It's easy because Python is the runs-on phase. So Python is a stack-based virtual machine. So I came up idea, why not build a virtual machine that accepts Julia syntax? So the idea is easy, but I don't have the ability to create iOS application. So I asked so recently I asked AI can generate lots of code. AI is great, smarter than I. So I use lots of AI to something like quad code codex, Cursor, DeepSeek, and Kimi, and so on. So and the result is we can use something like this. Okay, and this machine does not have Julia, but instead I have some called something like this. And this is interpreted routinely by me. So let's try this. Example manipulate.jl. Okay, this works. And the code is example manipulate.jl. Yeah, this is Julia code. Okay, Julia code runs on. Thank you. Okay, and let me skip the slide. What the subject Julia does provide is a package.jl. I don't know what to break the iOS policy. So I do not provide package.jl, network IO.jl feature, and file access just in case. And we do not support external process, something like run command, and C interface just in case. Instead, I support lots of user feature, something like this. And this diagram explains the subject Julia VM. The subject Julia VM covers web browser, mobile devices, and basic syntax, and customized third-party libraries, something like that, something like plots, and ordinary geometric equations, and symbolics, something like this. Yeah, it works. It should work. Oh, okay. This explains a counterexample Jacobian conjecture. Yeah, this is good. Okay. So I'm so greedy. There is, as you know, JuliaC.jl that compiles Julia code into executable library. So I also implemented Julia RS that is a transpiler, transpile Julia code into Rust. And Rust code is easy to compile with Rust C, like this Rust compiler. Okay, start talking question. So okay. I mean, this is, I want to say that SGulia is slow, but it's fast compared to Python because it generates typed code. So for those who are interested, and the devices, please contact s.terasaki at address.jp. So I'm waiting 12 testers. If please send an email if you have Android devices. Okay, thank you so much. If you have a question, your question and feedback is welcome.
Any questions? Oh, one over here.
So I noticed that it seemed like you said something about re-implementing some of those packages that were included. I'm guessing this is part of the answer to the real question I have. What did you do in order to get distributions.jl working on this? Because it is the real version of distributions.jl is relied on a lot of like compiled things from that were originally written for R, and that's an issue with installing distributions on a lot of like strange, not officially supported platforms for like real Julia.
Your question is install JL is difficult?
Yeah, I think the question is, what do you do about the JLLs that distributions relies on?
Instead of using JLL, I implement I use the last library instead. So, for example, if you distribute distribution.jl, it relies on this requires special functions. So special functions depends on some JL packages. So the part should be implemented in Julia or Rust.
All right, thank you very much. I don't think we have any times for questions, but if you have any more, please email Satoshi.
Thank you.
All right, our next top is by Patrick Hecker on arbitrary width integers and bit-packed structs in Julia. I'll let him take it from here.
Yeah, thanks a lot. So originally the title should have been every byte counts, but it seemed a bit wasteful, so that's why we ended up with this one here. So welcome to my talk, and it's about the two packages as mentioned, and let's directly start with a benchmark. So this is the most important slide, so if you fall into sleep afterwards, then you have seen how it works, so that's totally fine. So basically we have the regular struct, and normally we would use uint32, but maybe you come to the realization that 1 million values is enough for your variables, and if so, then a uint20 would be fine basically, and that's what basically the packed struct has, and it has this packed syntax. And then we collect a lot of values and just kind of access them by summing up the values. And you see here the time differences. And I know it's a bit complicated, so let's do a management summary. So the goal is basically that we find something which fits into the context window of the manager. So let's try that. So 2x is not too bad, I would say, and whenever you have such an improvement, then it's worth to think about what did you do basically so that you can repeat it the next time. So what did we actually do? We just avoided doing things basically because we didn't store things which we wouldn't access anyway, and that alone basically brought us the improvement. One caveat, if you can vectorize your things, then please do so. So if that are words SIMD-ified, GPU-ified, but don't use this here. Okay, so first package is emulated bit integers. Why using something like an int7? Because it can be more correct. So if you know that some values can't happen, the type system helps you ensuring that. For example, if you have a ring buffer, you want to have 16 elements in there, just using uint4 basically, and you're set. Don't need to restrict anything in the constructor. Maybe you have a fixed layout. There are all sorts of protocols, file formats, register addresses, whatever, basically, which you can ensure that you do the right thing there and or you need it to do the right thing. And obviously it's about memory. So ideally it uses less memory, and that was the 2x we have seen there. So it's not only about speed. Speed is nice, but there are also other benefits. And by the way, speed can mean that you need less energy, because if you run into idle, basically, your CPU can go in a much deeper sleep state. So that can also be helpful. That's the basic usage, basically, kind of as you would expect it, I hope. So you need this at emulate to get the type, basically. And from then on, you can use it. You can just add a value to it, basically, as you would expect. You can call type min, type max. Those are the values you would think about. You can add them, basically. And it wraps as if you would have a hardware type doing that thing. It is a primitive type, and it has no type parameters. What was a bit difficult define it like that, but we could move all the types into the element type, basically, and that enables it that it really looks like a regular integer. It has these two methods, basically, which are also public, so storage type of bits, the two functions, and with those, basically, you can check what this type is actually about. If you have multiples of 8, there is also the package bitintegers.jl, which I would recommend to use in this case. Then when you dig in a bit deeper, basically, for example, using the about package, you'll see the dependency tree, basically, where you have now the parameters, the uint8 and the 4 in the parent type, basically. Except that it basically does exactly what you think in types of parent structure. It prints the value as you would imagine, so the 1, 0, 0, 1, basically. And the bit pattern is basically we are using the lower 4 bits. Upper 4 bits are free or wasted, depending on how you look at it. So you might think this is slow. Actually, you probably don't because you've seen the benchmark, but why is that the case? Sure, we have more instructions because we need to mask away basically the 3 bits, but we have multiple ALUs typically, so we have multiple operations which we can do per cycle. And most of the time, things are idling around basically because we have some branches, some dependencies, whatever basically, and we can just slip in these and or shifts basically, and that's exactly what the processor is typically doing. So more instructions does not necessarily mean that we need to have more cycles. So it's often for free. You see it here in some typical usages. It's mostly a factor of 1, the green numbers basically. Obviously, if it can be vectorized, then it gets much poorer if you kind of work against vectorization with the additional instructions there. Okay, so second package is packed struct. And we see the example from the beginning, basically, where we had these 3 variables with 32 bits, where we actually only use 20 bits. So you get the upper layout, where you have those 12 bits of waste always in between. And the logic is totally straightforward. Let's pack everything together, basically. So reuse the gaps you normally have, put them on one side, basically, and just reuse it. In this case, we get down from 96 bits to 64 bits. Obviously, that needs even more shifting and more masking, but you know the trick. So that's how it looks, basically. Just adding that at packed. And then you get this special structure there with the PEG64 type. So it's basically creating one special field with a special type. And this type is now a tuple uint20, 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 basically. Getting around the way that we would need a variable number of type parameters. But Julia is great, and with that tuple, it's always one type parameter, and the tuple basically can grow. And you can access fields as you would expect. So you can just do p of x, basically, p.x, and the type is still uint20, so it acts like it really would be a native type. And how does it look? Exactly as you expect. So if we have a 3-bit type and a 5-bit type, the bits are just moved together, basically, to fill in the 8 bits, saving 1 byte. The question is, which field should be packed together? And that sounds totally trivial, but it isn't. These are kind of the requirements I came up with. And I think that I match all these requirements. However, I lack a proof for these. It's obviously not as easy as just being greedy, basically. So you can easily show that if you just move everything together, what can be moved together, you won't find the optimum. So example can be seen here, basically. This seems to be the optimization function for all I know, but I don't know whether it's the best optimization function, so there might be better ones. It's using dynamic programming, which I was totally unaware of how to do that. I learned a lot while doing that. And it's really, really fast, and this is all done during compilation time, basically. Might not be optimum, but should be already quite good. And here you see some examples for the groupings. So our 2020 grouping, you can see here, put everything into one group. With the 881, basically put all into separate groups. And then for 3, 5, 30, basically you can group the first one, but not the last. And sometimes you have degrees of freedom. For the last example, there would be multiple things which would be optimum, and you just need to decide basically what to do. And it's really like a struct. You can also add some padding in between if you want to with this pad type. And it basically has the methods as you would expect, using the functions from base as you know them. Obviously, there is a limit of what can be done in a package. So as soon as you start with the package inspection and really going to the non-overridable types, then basically it becomes obvious what's really behind that. So you can't hide that one. Would need really support in Julia itself for doing that one. Luckily, Max already started getting some functionality into Julia upstream. So if you have a master, then you can actually do that now. You can define the types, but you can't use them too much currently. It's already working on improving things there, adding things there. But for the moment, there are no methods yet. But I'm more than glad, Max, when you make my work here obsolete, because I think this really belongs into Julia itself. So takeaways, you have these two packages now available, basically. They are registered, they're in Julia data. Just use them. You can emulate with the macro, you can pack with the macro, basically. And you can get faster performance with just 2 macro calls. I think that's probably worth it. However, if you still are not sold to that, I actually have a proof for my title. See? Thanks for your attention.
All right, any questions? Oh.
Thanks for the talk, it's very cool. Maybe I'm just lacking some understanding, but so you say that there are these, say these ALUs that are sitting dormant, usually unused, but then at the same time that having the packed representation is going to be more energy efficient because it's able to run faster, but isn't it also going to, say, run hotter by running more of the units at the same time?
Yeah, actually it is. So it's needing a bit more instruction. However, that is not taking too much power typically. And as you are faster done, the whole system can go into a lower power state, and you'll save more power with that lower power state, with that additional time, as you lose with that bit of extra work, basically. And therefore, it's a bit counterintuitive, but overall, it can actually save energy.
Any other questions?
Excellent talk. This is really cool stuff. So then is the assumption true that because of the packing, then we would also save memory equal to that performance gain that you showed us in your simple example?
Yeah, I basically, it depends on your specific problems, but in this case, we had memory saving from 1.5x, basically, going from 96 to 64. This depends on how cleverly you can use your width, basically, to pack them into something which is really a native type in the end. In that example, we packed it to 64. We only needed 60, so our overhead was really small, but there are examples where you will end up at 65 bits, and then obviously it won't be that optimum. Depending on your padding and your alignment rules, basically, it can blow up to 128 bits, so it really depends on your case.
So then can we assume that it works in the other direction? You know, instead of packing down, can I expand out?
It should never be larger. because it detects that basically and then just keeps the things basically. That is one requirement. However, it might be then a bit slower in some cases. I haven't tested that. That would be interesting.
Alrighty, thank you very much. Let's give a round of applause one more time for our speaker.
Because people look at the schedule. And
All right, the next talk I believe is canceled, so in 15 minutes we'll meet back here for Christopher's talk. All right, I'm going to go ahead and announce our last 30-minute talk of the conference before State of Julia in the tent, 15 minutes afterwards. This is Forward Mode AD, specialized for second-order derivatives by Christopher Carlson.
Thank you for the introduction, and thanks for coming here listening to my little side project. I work for Julia Hub. I work on Julia itself, the package manager, doing some releases. So this is a little bit I did sort of on the side for fun. So let's talk first a little bit about automatic differentiation, what that is. So basically what we want to do is to obtain numerically like exact, pretty much as exact as we can, derivatives of some parts of our programs, but we don't want to implement them manually. This would save us time and avoid bugs and so on. Coding up derivatives, and especially second-order derivatives, can be quite tedious, and it's easy to make some small mistakes somewhere. And AD is not really symbolic differentiation. If you think about calculus class, when you wrote down the whole symbolic derivative, so you're not building up like a huge expression. It's a different way. There's many different types of AD. One is called reverse, one is called forward mode. I'm not going to go into the details, but this talk is going to be about forward mode. And we don't really talk about reverse mode here. No, this is going to be forward mode only. So the simplest thing we can do if you want to do some kind of derivative without having to calculate it analytically, we just look at our Taylor series, we expand it around some points. We can see that the derivative up to some order here is roughly equal to, if you take a little bit step to the right of your point, and then you divide with that. That's dice. Now the problem here is you have a big h, then you have a lot of error from this dropped terms here. But if you have a small h, then the subtraction there will be almost 0, and you will have cancellation in floating point. And you also have to call f twice here when you do this. So. But we can try it out if we define some function here. We can define this finite difference operator. We define what the exact value in some point is, and then we calculate this with a big H, and we get some error, and we calculate with a small h, and we get some other error. And if we then plot this relative error here on this plot, depending on the step size we take, we can see that for very small h, we get large error. For very big h, we get a large error, and then there's some like Goldilocks thing there in the middle where you get the best thing. But the question is then, can we do better? So one thing that we can introduce something called a dual number. So if we first think about a complex numbers, define it as two components. We have I squared is equal to -1. We have some imaginary slot extractor that takes out the imaginary part. So if instead think about a dual number here that also has two parts, but instead of having the square be -1, we say that the square should be 0. And what happens? Okay, let's put in this number into the Taylor series, and we can see here that these higher order terms now becomes equal by definition of having the square of this epsilon term may be 0. So if we now solve for the derivative, we can see that if we compute the function here with our dual number at some h, and we divide by h, and we extract this epsilon part, we get the derivative exactly here. There's no truncation or anything. And we don't need to do any of this subtraction stuff, so we're not running into cancellation. But then, just as for complex numbers, we have to define operations on these dual numbers. So as one primitive, for example, how do we calculate sinus of a dual number? Well, we can just look at what the definition is. We need to calculate the real part, and then the epsilon part here, which is h times the derivative. So h times the derivative of sinus gives you this one. So that's how we calculate sinus of a dual number. Now, for example, you can do the product rule, and if you expand it, you use that epsilon squared is 0, you get something like this. And if you look at this, it looks a little bit like the product rule, where you have the derivative times the function value, and then you have the other way around. So if you want to calculate the derivative, then you can just set h is equal to 1. So h is 1 here, and then you just read the derivative off after you've computed this. So you evaluate this function here, and you take the epsilon part, and there's your derivative. So let's do like a super small implementation of this in Julia then. So we define this dual number, real part, epsilon part. We define plus, multiplication, as we showed before, sinus. We have the epsilon part there, which is derivative, multiply with this little epsilon. And then we say the derivative then is evaluating f at this dual point, and then we take this epsilon slot. This is sort of exactly in Julia code what was in math here. And then we can define some function. We take the derivative of this function at some point, and we compare it with the analytical value. And for this one, it agrees up until the very last digit even. And we can look at the code warn type here, and you see we have optimized, everything has been inline and optimized, so this is actually very performant as well. And for reasons I'll talk about later, I also talk about the data layout here. So we have the layout of this number is, first we have a real value, and then comes the epsilon value. So what if you want to do higher order derivatives then? Well, we just define the derivative function, which is Julia code, and we know how to differentiate Julia code. So we can define a second derivative. It's just to take the derivative of the derivative, right? So then we have to do a little bit of generalizations here so we can put a dual number inside another dual number. Before, in my earlier definition, I just hard-coded float 64 series and so on. Now I'm going to parameterize it on some type, and then I'm going to put a little bit more. Instead of having a hard-coded 1.0, I do 1 here, I define 1, and so on. But just a very standard generalization of the number. Then I define the second derivative here, and now I can compare it to the analytical. And for this case, it was correct up to the very last digit as well. And if we think about the data layout of these dual numbers, when they nest into each other, we get the value here. Then we actually get 2 components, that is the derivatives. And then the last one, we have the second derivative there. Then we might want to do Jacobians, where we give in a vector and get the vector of some other size back then. So if we plug this into the Taylor formula, now we have bold faces here to show we have vectors. Instead of having a derivative, we have a Jacobian matrix here. And we can just do the same with our dual numbers. We plug in a vector of dual numbers. And then if we look here, we have a Jacobian times a vector product. So depending on how we pick these epsilon components, we're going to get a different value. And one way we can do it is to pick these basis vector to pick out one column of the Jacobian at a time. So Julia code for that would then be just to loop over here, and we seed for the vector we want to pick out. We call the function with this seed then, and then in the end we just push it all together and get our Jacobian. And this can look a little bit similar to how you would do it find a difference. You would also loop over, and then for the I you would do a little small perturbation there. But for us instead we do a small sort of epsilon perturbation. Now the problem here a little bit is that you're calculating this f one time for every column. So the question is, can we do better than that? So we can extend this to something called chunk mode, where we, instead of having a single epsilon in every dual, we extend this so we can have multiple epsilon components here. So we extend this by a type parameter saying how many epsilon components we have, and we replace this with an n tuple, and then we have to fix up a little bit our definition. So in multiplication, now we have a value here times a vector, so we're doing these dot broadcasted operations and so on. But yeah, when we had that defined, we can calculate multiple columns of the Jacobian at the same times. So one thing we can do is we can calculate the whole Jacobian in sort of one shot by having these epsilon components be large enough that they span the whole space, sort of. And this is good because since we only call the function once, we have to only call, for example, if I used the function I defined earlier that had sinus in it, we only have to call cosinus once as well, but before we had to call it for every column. The problem is if we make this n too big, here we have a tuple. If we make this very big, then we're going to run out of registers in the CPU and so on. So typically you want to have this sort of just at the Goldilocks perfect size, and I'll talk a little bit about that later, how you pick this. But for this type of number, the data layout would then be a value, and then you would have all the epsilon components after it. So if we want to look a little bit about how the code that would do, so if we had calculate the whole Jacobian in one shot, we just define our dual numbers, we loop through all the columns, and then we create this big seed for them, which has the size of the Jacobian, and then we call the function once. We pick out what we need, and then we put it into a Jacobian. And we can use this code and try it out. And yeah, we can call the Jacobian on some function here, get the matrix out. Now with the chunked mode then, when we're not doing the whole thing in one go, but we're having sort of step by step, we're instead just doing one chunk at a time instead. I'm not going to go through the code here, but it's like instead of doing the whole thing in one time, you do it step by step. And for every step, you have to call the function one time. And the problem here is, you know, you have very large dual numbers that can be bad. The problem here is that you have to call f more times, so it's like a trade-off. So let's say we want to do second-order derivatives. Well, the Hessian is the Jacobian of the gradient, and we know how to do Jacobians, so we can do gradients, so we can just define our Hessian then to be the Jacobian of the gradient. Very easy. So if we have a function here, then we can calculate the Hessian. Didn't have to do any complication just by the definition of the Hessian is. And this sort of dual numbers then nest just like we did in the scalar case, what we call the derivative of the derivative. And the memory layout for this then would be the value here, then you have the gradient, and then you have the gradient components here once more with the second order derivatives slotting in here just next to them. So the point of this talk then is that there's another number called a hyperdual number, which is a bit different from dual numbers, which you can use to calculate second-order derivatives directly, not by doing this nesting. So the dual numbers, you have that this epsilon squared was 0. Then you can define a hyperdual number that has actually more of these epsilon components, where you have that the square of these different ones is still 0, but the cross between them, if you multiply these two epsilon components on the cross here, that's not 0. So once again, we do the same thing. We put this into our Taylor series. If we define this delta thing and we crank through the whole thing using these rules, we end up with a definition of a hyperdual number, which looks like this. So it has the derivatives here, and then you have a little bit more complicated expression for this cross term here, which includes the second derivative. And this part here is actually the second order chain rule. And just like we did with the dual numbers, we have to define operations for our hyperdual number then. And we do that by looking at the definition here, what it says. So if we want to do it for sinus, okay, we see we have to do sine on x, then we have to a times the derivative, okay, b times the derivative, okay, c derivative, and then second derivative, so in here, minus sinus with the ab there. So now we have a primitive there, we have the product again, and then to get the second derivative then, we just put a and b is equal to 1, so then this one survives, and we put c equal to 0, and this one dies. And the only thing we have left then to get the second derivative is just read off this cross slot, and we get out the second derivative. So now we have the theory. Let's do the implementation then. So just like before, we have the real value. We have these two epsilon. We have the cross term. We define multiplication according to what we found it to be. We define sinus here according to what we had it to be here. And you can do some little bit of automation. You can calculate sinus and cosinus at the same time. Instead of doing it separately, saves a little bit. And then you can say that the second derivative then is to call f with these hyperdual numbers, where we see it with 1, 1 on the a and b here, and 0 there. And that's the whole definition. And let's try it out. Define the same function we did as before, and now we can do second derivative. And we get exactly the same value as we did with the nested dual case. And the data layout here is kind of similar. We have the value, then we have these two so derivative numbers, and then we have the second derivative slot here. So if we want to calculate a full Hessian then, which is a matrix, we can do similar to what we did with the Jacobian. We loop through, and we put in the seeds that picks out exactly the Hessian component we have by seeding the correct components here. And we're actually, here we're using some symmetry of the Hessian, so we can loop over just the upper triangular block here instead of doing it of the whole square. And if we do that, we can call the Hessian and we get the value again. But just like before, we're calculating f here for every entry, which is wasteful. So we do chunk mode. With the dual numbers, we had a single vector chunk. But now instead we have sort of a matrix chunk. So we do a little bit of generalizations here. We're saying that these epsilon 1 and epsilon 2 can be vectors, And this in epsilon 12 then is kind of like a matrix. Here's a tuple of tuples, but it represents this matrix part. And then, like before with the dual numbers, we can do a whole Hessian in one call by seeding correctly and then calling it once and then extracting the whole Hessian at once. And we can do it and it works. Or we can sort of do it in chunked mode where we compute block by block by block. So here I have the figure here which shows like, okay, first we calculate this block, then this block, then this block, and so on. And then we have to call f a few more times, which we're in the loop here. But these hyperdual numbers don't get so big. And if we look at the definition of these hyperdual numbers, they can grow quite quickly here because the size of this cross component is n1 times n2. So let's say if you're doing, it's like if you have 8 and 8 of these, then all of a sudden you have 64 numbers in here, which can be quite big. So then if we compare the nested dual numbers and hyperdual numbers, then they have the same data in them, but the order that the data is stored ends up being a bit differently. So for the hyperdual number, we have the value, then comes the two epsilon 1 and epsilon 2, and then comes all the higher order sort of derivative parts like that. But for nested dual numbers, we have the value, and then we have one of these gradient part, but then they sit like this instead. So you have one Hessian part or one second derivative part coupled with one single gradient part. And we'll look a little bit later on what happens due to that. So what are the implementations of this? Well, first we have forward diff, which is sort of the GOAT in Julia of forward mode AD, greatest of all time. It's been there since 2015. It always works. When your reverse mode package breaks because someone removed a comment in Julia or something, forward mode still works, and it's going to work forever. Yeah, you can just load forward diff, calculate a function, and then you can compute the derivative, Jacobian, gradients, Hessian, very, very easy. Just a little bit of a detail. It has like this, it's different from what we did with our dual number. It has these tags, so it can check if you're like doing two derivatives that's gonna intersect and avoid those to get confused there. You can pre-allocate this Hessian config, which is gonna hold like pre-allocated data, so you don't have to allocate. And with that, you can also set the chunk size. And the implementation of Hessian in forward, if you go into the source code, it actually does exactly this Jacobian gradient. You can see it like calls Jacobian gradient in there. There's no like Jacobian vector product or Hessian vector product in the API, but fortunately we have differentiation interface. And with that, you can easily just import differentiation interface and forward diff. You can say that you want to use forward diff as your backend, and then you can calculate the Jacobian vector product in some direction, or also the Hessian vector product. So a little bit of an API miss there, but it's easily remedied with differentiation interface. Now comes sort of the point of this talk, which is hyperhessians.jl. And this is just an idea I had to be like, let's say we made an AD package based on hyperdual numbers, and then compare with the forward diff nested duals, like what would happen? Would it be slower, faster? Just as a fun experiment. Now the first commit I did for this was in 2021, so it's a Vibeless project. I wrote it by my own fingers. I got some results showing that it seems to be faster, but I didn't really have time to polish it and make it into something actually useful. So my curiosity was stilled, and that was enough at that point. But now with this agent coding having become a bit better, it felt like now I could actually polish it up and make it into something that might actually be useful for other people. So the API then for hyperhessians is kind of similar to forward diff, except that it only supports the second order stuff. So same, you can load it, define some function, some input, and then here there's a direction too for doing the VP stuff. So then you can calculate the Hessian vector product. There's also this quadratic forms, V times H times V. You can provide Hessian config, say what chunk size you want to use. And there's also a little option here, which is called simd is equal to true. And if you set that, it's going to use explicit simd instructions from the simd.jl package. And we'll see later that that might be good to do sometimes. Yeah, you can get the lower order stuff for free because they sit in the number and so on. You can also do threading with this if you have a really big function and you want to call this, you can calculate these blocks threaded. There's a threaded Hessian config, and if we do that, and we look at sort of the scaling, I mean, it scales pretty well because it's such an embarrassingly parallel thing. You just calculate the blocks in parallel, but of course, this function here call must be safe to call concurrently, and so on. It's also registered in the differentiation interface, so you can load that, import the package, set it as a backend, and then you can just call Hessian with a backend and doing everything else you would with the differentiation interface backend. So let's look a little bit on benchmarking then. So one question when I was going to benchmark this is like, what chunk size am I going to pick, and how should it be fair? And I figured the only way it can be fair is to sort of benchmark for both forward diff and hyper-Hessians the best chunk size for every function, for every input, and just use that sort of to get the best out of both and then compare that. So to do that, I wrote a little package called chunk picker, and you basically provide an AD backend like hyper-Hessians or forward diff, provides the function, you provide the input vector you're going to use and what operation, and it's going to benchmark for different chunk sizes and for hyper-Hessian case with explicit SIMD or not. And then it's going to give you back what was the best chunk for this. And here it happens to be that they wanted a chunk size of 8 using explicit SIMD. And I mean, you can see it's quite a big difference here. If I just put a chunk size of 8 and I didn't enable the explicit SIMD thing, I almost had a 1.7 times slower. So I think it's worth doing this thing if you're going to run some big thing that uses AD to spend a little bit of time measuring what chunk size is the best. And you can use this for forward diff and for other operators. You want to check like the HVP or in the forward diff case, the gradient Jacobian and so on. So I did some benchmark first on my laptop here with some different functions and different input sizes, and the speed up here is like the relative to forward diff. So if this is higher than 1, then hyper-Hessians is faster. So it seems for this case, we had a bit around 2.7 as the geometric mean faster for some different function, different inputs. I also tried it on another machine, which has a AVX 512 system, and I'll talk a little bit more about why that later, but it also seems to be around 2.5 times faster. Also did some HVPs, and total was around 1.6, and on the bigger system it was 1.8. These are more like toy examples, but we've also run it on an actual finite element problem where we're using second order derivative. So we have some sort of free energy definition, and then in finite element you loop over your elements and you compute some things. And here we're computing like an element potential where the code here doesn't matter very much, but we're accumulating stuff. And so I wanted to try that as well, to not only have toy examples. So I did the chunk picker thing, and turns out here that we should pick a chunk size of 2 for both the forward diff case and the hyper-Hessian case. And in the tutorial, it was actually just hard-coded 4 there, which was about 50% time slower. So, but again, we got around 2 times faster than forward diff. So I don't know, for the people who were here in the last talk, there was this type of slide, it's saying 2x. So that's sort of the whole takeaway, I think, for this benchmarking thing is seems to be around 2x. Yeah, easy to remember. And just as a little bonus, I was interested in this, that you have the same data, but it's laid out in a different way and what effects that has. So I'm showing this slide again, where I'm showing how the data is laid out for the hyperdual numbers or for the nested dual numbers. And just as a case, I benchmarked multiplication for different chunk sizes then. And on the left here, and to say these are doing the same number of flops here, exactly the same. So on the left, this is on my MacBook, and to the right, it's on the AVX 512 system. And you can see on the MacBook here, they're more equal, while on the AVX512 system, we actually have more than 4 times difference for some cases here. And this is a bit interesting here, because here we have that the nested dual and the hyperdual are exactly on top of each other here. But then if we enable the explicit SIMD operations, then we have a 4.5 times speed up for this 2 case. So somehow I guess the auto-vectorizers really makes a mess out of thing here or something. And then for the 8 case, where you have exactly, you fit your data into this 512 register, it seems that the auto-vectorizer gets it right, and there's no difference between the explicit SIMD instruction versus the normal ones. I was at the high performance computing workshop, and they talked about using liquid, which is a way to measure performance counters, because this time here is just kind of one-dimensional. It only says like 4.5, okay, but 4.5, like why? So using some performance counters, I also ran that using A times B here, and you can see like how many flops it calculates and so on. And we can see that we have the same number of flops here, but in the hyperdual case, either if we're using explicit vectorization or not, we almost have 80% of them as fused FMAs, while for the nested case, there's none of them. There's also many more instructions, many more of these microcode instructions for the nested dual case. We have more access to the cache. There are also many more integer operations, which is for the nested dual case, which is kind of interesting because we're only doing floating point math here, but still we have so many integer operations because I guess there's like indices having to be calculated and so on, while with the explicit SIMD vectorization, barely doesn't have any integer operation, just blasts through doing floating point stuff. And if you look at the actual cycles, it's also significantly lower for the hyperdual numbers than the nested ones. And almost like a quarter of these micro-ops are spent doing integer stuff than doing actual floating pointing stuff. So to conclude a little bit, hyper-Hessians, this is the package I presented here, can give some speed ups versus forward if, especially if threading makes sense, because there's no like built-in threading thing in forward if. If you're using a differentiation interface already, it's very easy to try it out. You can just change your backend. And spending a little bit of time choosing the chunk size can be worthwhile. You saw there was quite a big differences which one you picked. And sort of some general thing is like, I mean, everyone probably knows this already for 20 years, but counting flops is like dead, super dead. It doesn't matter at all, basically. Auto-vectorizers can sometimes make like a real mess of things, so you can consider using simd.jl, which provides like explicit SIMD intrinsics written in LVM. Think about the layout for your data. If it looks like the top one, where everything is sort of separate, that's probably good. If it looks at the bottom one, where it looks more complicated, that's probably bad. And experiment a little bit with performance counters like Liquid, there's Perf, and on Windows, I guess you use VTune and so on. And I think that's interesting, and not only looking at time, because time can be polluted by noise and just one value, while performance counters give you much more richer sense of what's going on. Thanks.
All right, we got some questions.
Yeah, thanks a lot. Super interesting. So sorry for asking very basic questions. So if I have a very high dimensional problem, let's say 1 million because it's a big image, does it make any sense to use forward diff, or does it scale much worse than reverse mode differentiation? And also what one might want is this Hessian vector product, because it's actually the same as the directional, how do you say, derivative, yeah?
Yeah, for that big sizes, you probably want to use reverse mode, especially for Hessians, because forward mode is good when you have, let's see if I get the order right now, if you have a small number of inputs, while the reverse is better in the other directions. So for the big sizes, like you mentioned, I think reverse diff is going to be better. But one other thing I could put on this slide, someone said like if you're profiling, you have one leg up compared to the one who's trying to like simulate things in their head. So you can just test and measure it. That would be my advice. Always measure. Computers are very, very complicated now, but yeah.
Yeah, thanks for the talk. You've mentioned forward diff's tag system. Does HyperHashions have one? And yeah, or can it avoid it?
Yeah, it does not have one because it's kind of rare that you're gonna have two second-order derivatives collide like you do with two first-order derivatives, I think. So I didn't really see a reason to put it. If someone puts a reasonable example why it should have it, then I can probably put it in. But I thought about it, but it didn't seem like there were realistic cases where it would actually be a problem in practice.
Do you think this also affects the performance of the fusing, for example?
No, it should not. It should all be just compiler bookkeeping. It shouldn't be any difference in the...
Okay, thanks.
Here, I'll just bring it over here and then you guys can pass it around.
Thanks. Yeah, thanks. Oh, okay, yeah. Yeah, I was wondering if the performance benchmarks were done by disabling symmetrization of the Hessian. Because I think forward diff does not use symmetry.
It does
for
not,
the
no.
Hessian.
So you have, as I said, the only thing forward diff does is this. Here, it does this nested Jacobian with gradient, so it does the full thing. So there's probably work that could be done in forward diff to improve it. And if you did that, you would get the... You don't really get 2 times performance because you have to calculate the diagonal as well. As the size goes to infinity, you're going to have like half-half, but the smaller it is, the more this diagonal matters. But that would, HyperHashian would probably still be faster, but it wouldn't be such a big difference.
I haven't thought through whether this makes lots of sense, but dreaming big, what if we nest this and go for fourth derivatives? So have you tried that out, or does that not work? I mean, the question is, when you do that, as you just said, you have this, you only do the upper triangular of the matrix, and maybe that will not work when you nest it, but yeah, have you tried it out or thought about it?
I haven't thought about it. I guess you would sort of get like an upper triangle in 40 space or something.
But so I mean, there are applications where you need or would like fourth derivatives, and so the question is whether this could also help there, compared to just using forward diff. And
it's interesting. I cannot say, but it's worth trying. But maybe then you would actually be better off, because I just talked about how, nesting these numbers are not the greatest. So maybe at that point it would just be better to define your, let's see.
Hyper
thingy here.
Okay.
All right, I think we have to go ahead and head over to the keynote starting in the tent right now, the state of Julia. But if you have any questions, hopefully people are around afterwards to ask those. Thank you so much.